Okay, so let's get started now. Am I audible to all of you?
Yes, sir.
Okay, thank you.
Yes, sir.
So at the beginning of the course, I was giving you an example about this bank balance thing, right? So in this chapter, we are going to study why that kind of a problem can happen and what can we do to prevent such problems, right? So let me speak about that problem again. So your bank balance was 10 rupees. Okay. Now you want to deposit 5 rupees and let's just say your credit card company wants to deduct 5 rupees as the bill for that month. What happens if this process is allowed to happen simultaneously? So when you are trying to deposit 5 rupees, you will read the balance into a temporary variable, right? You'll always do that. So your temporary variable would be 10. Then you would change the temporary variable to 15. Then you would write it back. To the bank balance. Okay. Similarly, so let's just say before you could write it back, if your process is suspended here by the scheduler, for example, that says, okay, stop right now. Other processes are waiting to run. So before it could write the temporary variable, which has 15, back to the bank balance variable, which is a shared variable. This is shared. This process starts running. So this process would again read the bank balance into its own temporary variable because the value of 15 has not yet been written back to the bank balance variable. Your credit card company, which is trying to deduct 5 rupees, would read 10. Then it would set its own temp variable to 5 after subtracting 5. And then let's just say it is able to write it back. Okay, so now the bank balance becomes 5. Then this process terminates. This process starts resuming from the point where it had left off. So the temp variable there is 15. And now this is written back without paying any respect to what this process has done here. So this 5 will be removed and 15 will be written back. Now you tell me, is this 15 the correct final value of the bank balance? So if you begin the value of 10, add a 5 and you subtract a 5, what should be the final value?
10.
10. But now the value is 15. It's not correct. Similarly, the other way around can also happen. What can happen is, now before this person can write it back, okay, this process is stuck at 15, this process is stuck at 5. Then this process starts running, writes a 15. This process starts running, writes a 5. So the final value would then remain as a 5. That's also bad. It's bad for you. Here, if it's 15, it's bad for the bank because you have extra 5 rupees. If it is 5, then it's bad for you because you have less money now. These kinds of problems are called as race conditions. Okay, they look like a race. Now, these kinds of things happen if there is a shared resource. And two or more processes are trying to modify. Okay, they're all trying to modify this shared resource simultaneously. Not even simultaneously, concurrently. Okay, I'll tell you the difference between concurrency and parallelism after this. Okay, concurrently, if these processes are trying to modify the shared resource concurrently, then a race condition can happen. And what is a race condition? In which the final state of the shared resource depends on the sequence in which these processes modify this resource. So here, whether it would end up being 5 or 15 or the correct value of 10, the correct value of 10 can happen if the left process completely finishes executing, writes the value back, then the right process can read a 15, decrement it to 10, then write it back. Then the correct thing will happen. Or the other way around also. If the right process finishes executing, writes the 5 back, then the left process reads the 5, increases it to 10, then writes it back. Then the value will remain as 10. So these are all race conditions. The final value of the shared resource depends on the sequence in which these processes run. And these kinds of conditions are called as race conditions. Is it clear to all of you?
Yes, sir.
Okay. So processes can execute concurrently. Let me give you the difference between what concurrent execution means and what parallel execution means. So many of you and me to some extent at one point, I used to think that concurrency means parallelism and they both mean the same thing. That's not true. So let's see, if there is a single CPU and there are two processes running. So P0 runs for a little bit, then it is stopped by the scheduler. Then P1 runs, then P0. They keep running like this, one after the other, in a round robin fashion. Then P0 and P1 can be said to be running concurrently. They are not running parallelly. When P0 is running, P1 cannot run because there is only one CPU core. But can this result in a race condition? Yes, this can still result in a race condition. Always think about the banking example. So if P0 read the value of 10, incremented it to 15, before it could write back, let's just say it is suspended. And P1 reads 10, it decrements it to 5, before it can write it back, suspended. Now P0 comes, writes 15, then P1 comes, overwrites that by 5. Okay, can happen. Not running parallelly, not running simultaneously, but running concurrently. If multiple CPU cores are there, CPU and NCPU, then P0 and P1 can run parallelly at the same time. Then the same problem can happen. Okay, they're both accessing the same shared memory. It can still happen, that problem can happen. But it looks kind of obvious that it will happen here, but it is not, does not look very obvious that it will happen in this case. Okay, so it is fair to say that all parallel processes are concurrent by default. Okay, all parallel processes are also concurrent. But not all concurrent processes are parallel. For example, here, these processes are running on one CPU core. They're running concurrently, one after the other. None of them are finishing what they're doing. They're both accessing some shared memory. They're in the code which is modifying that memory, but they're getting stopped in between. The other process runs for a while, then this process. So they're running concurrently, but they're not running parallelly. They cannot. There is only one CPU core. So all parallel processes are concurrent, but not all concurrent processes are parallel. But for a race condition to happen, all you need is the condition of concurrency. It is not necessary for the processes to be running in parallel. So if someone tells you that, oh, just with this one CPU core, all of these race conditions, they happen on multi-core processors. They cannot happen on single core processors because you cannot run code parallelly. But it is not necessary that the code is running parallelly. Even on single core processors, race conditions can happen. Are you all able to convince yourselves that that is the case? Yes, no, anyone? You need more explanation? Hello?
Yes, sir.
Yeah. Is it making sense to you? This idea? That how concurrency does not need more than one CPU core? How that at one point of time only one process could be running, but it does not finish what it is doing. For example, in this example, if the thing that was depositing the money, if this would finish doing what it was doing in one shot, then this thing on the right side would start running. Then these problems would not happen. But that is seldom the case. The scheduler can stop this process here before it can write back. Then it can run this one after the other in a concurrent manner, not necessarily in a parallel manner. If they're running parallelly, then sure, it is very obvious that problems can happen. But even if they're not running parallelly, even if they're only running concurrently, these problems can happen. Okay. Because these processes can be interrupted at any time when they have only partially completed what they have been doing. And if that they access shared data concurrently, then the data can end up in an inconsistent state, which we saw in the previous example. So to maintain data consistency, you need the processes to cooperate with each other. So that if process P0 is accessing that memory, then all it has to do with that memory needs to get over. Only then P1 should start accessing that memory. P0 should not be stopped in a state where it was in the middle of accessing this memory, doing whatever it was doing with this piece of memory. Then P1 should not be given a chance to also access the memory while P0 is still midway trying to change this piece of memory. No. So they should cooperate that way. That okay, only after I am done, you should start accessing that memory. Before that, don't do it. Okay. So let's look at the producer-consumer problem and see how this can also result in a race condition. Just give me one second. So in the producer-consumer problem, you usually have a buffer. Okay. So let me draw a buffer of size 5. So the indices are 0, 1, 2, 3, 4. There is a shared variable called as counter. Okay. This tells us how many elements in the buffer are full. Usually this buffer would be empty to begin with. But there are two processes running, the producer and the consumer. The producer produces one item at a time and then puts it into the buffer. The consumer consumes one item at a time from the buffer. Okay. And the counter variable is a shared variable. This is a shared variable. Shared between whom? The producer and the consumer. And it basically stores the number of buffers full at this point of time. So let me tell you, for example, in this example, buffer size can be made equal to 5 because that is the size of the buffer. 5 elements are there in this array. So if the counter is equal to the buffer size, that is, all 5 elements of the buffer are filled up, can the producer do anything? Should it produce anything more? Yes or no?
No, sir.
No. So what it would do is it would just keep spinning inside this while loop. Like this loop is just one line. It ends right here, right? There is a semicolon, there is no block. So do nothing. Just keep being inside this while loop, round and round, until the counter is equal to the buffer size. Okay. Now who can change the counter? Because the producer cannot do anything. It is stuck in this while loop. The consumer can. The consumer is probably running. It can do counter minus minus. Okay. Because it has consumed something. So there is now one less item on the buffer. So the counter at some point will become less than the buffer size. When it so becomes less than the buffer size, let's just say 2 items were consumed by the consumer. Now the counter is 3. When the counter becomes 3 or 2 or whatever, some number less than the buffer size, this while loop is not, this while condition is not true anymore. So it's gonna go to the next line. So both the producer and consumer, they maintain some kind of variables like in and out where they store where they had produced the last item. Okay. So if the producer had produced the last item in this and this, then the next item should go into this index 2. So in would basically be pointing to that. So one more item will get produced there and in will now point to the next one. If another item gets produced, it will go here, in will point to this. Then something else gets produced, then in actually is in plus 1 percentage buffer size. So in can never be equal to 5. It will actually go back to 0. Okay, it will just keep going inside this range because this percentage buffer size is there. Just a pointer to say where to put the next item. That's all. Once the item has been produced, and counter plus plus because something got produced. So we have to increase the counter because one more cell is filled up right now. Is this program making sense to all of you?
Yes, sir.
Yes, sir.
Okay. What's happening in the consumer here? So the consumer cannot proceed any further if the counter is 0. Why is that? Can someone tell me?
Sir, there will be no products.
Correct. If there are no products, then the consumer cannot consume anything. Very good. The buffer is empty basically if counter is 0. Okay. But if the producer produces something, it is going to do counter plus plus as we saw here. Okay. So let's say the value of counter is 2 right now. Okay. Let me draw the buffer again. So when the counter becomes 3 or whatever, or 4, or even 1, it's going to come to the next line. It says it will consume the item from wherever, let's just say this is where the last item, this is where it had read the last item from, this one. If the consumer had read the last item from this item, now it will try to read it from this item because the producer is also producing it sequentially. Like 0, 1, 2, 3, 4, then 0, 1, 2, 3, 4. So let's just say the out variable is pointing to this. So it is going to consume that value into the next consumed variable. Out will now point to the next location and counter minus minus will be done to kind of signal the producer that, okay, more space is there for you now because I have consumed something. Clear? You get an idea how this works, all of you? Okay. So what problem can happen? Does this read this slide and tell me if this is the exact same thing as the banking problem? Is this understandable to any of you? What's going on? So basically, whenever you're trying to increment or decrement or work on anything, you basically copy that value to one of your registers, work on that register, and then write it back. Okay, that is exactly how things are done on processors. You cannot directly change the value at a memory location. You get the value, work on it, then put it back. Okay, is that much understandable to you from this blue lines?
Yes, sir.
Okay, and counter minus minus is the same thing. This is one process. The counter plus plus is done by the producer, and the counter minus minus is done by the consumer. So as you can see, these things are not atomic. I mean, they're not one step. These processes can be stopped at any one point of time. They can be stopped before this here. They can be stopped here. They can be stopped here, and they can be stopped here also. They can be stopped anywhere at any of these four. If they're stopped after the last statement, then it is okay. If they are stopped at the first point, also they're okay. But if they are stopped at this point or this point, then strange things can happen. Like for example, look at this sequence of operation. Okay, the producer does these two lines. Okay, so the counter is 5, let's just say. So it is read into register 1. Now trying to increment it, so that the register becomes 6 now. But you see that producer was not able to write anything back. Before it could write anything back to the counter variable, S2 started executing. Then it read the value of counter, which is still 5. Producer has not been able to write it back yet. It reads 5, reduces that to 4. Then the producer runs. What it resumes where it left. It had a value of 6 in the register. It writes 6 back to the counter. Then the consumer runs, writes a 4 back. The final value is 4, which is not correct. Started with 5, 1 increment, 1 decrement, so that remained at 5. Same problem, the banking problem all over again, is it not?
Yes, sir.
Okay. Why did this happen? Because when you're trying to access this counter variable is shared by two processes. So whenever you start doing something good with, ensure that you are done before some other process starts running and tinkering with the same shared variable. If you mix them up like this, then these kinds of inconsistencies or race conditions can happen. Okay. So for example, if this blue lines had executed in one go, if this blue line had come here and all three had executed at the same time, then this problem would not have happened. Are you able to convince yourself of that thing?
Yes, sir.
Okay. Okay, so let's look at the critical section problem. This problem is an abstraction of how these kinds of processes usually are, in which there is a section of code where these processes try to access shared variables. Okay, and the requirement here is that when there are two or more processes trying to access that shared piece of memory in their critical section, that section is called as the critical section. These processes kind of look like these. So there is a critical section. This is where they try to access shared resources. So if there are many processes like this, then only one process, zero or just one process, would be allowed to be in its critical section at any one point of time. You cannot have more than one process in the critical section. Okay. So to be able to enter the critical section, you'd have to ask permission in the entry section. Many processes could be running in this section, but only one process will be allowed entry. When that process is in the critical section, the rest of the processes would have to be in the waiting state in the entry section. There are various ways to do it. We'll be studying all of that in this chapter. When that one process which was allowed entry into the critical section is done, it would come out, and this is where it would notify in some fashion that I'm done with my critical section. Someone else can enter the critical section safely now. Then it does whatever it has to do in the program. Then it again comes back, asks for permission to enter the critical section. Are you all able to understand this general structure of processes that try to tinker with shared resources, and why this is a problem? This is a problem we are trying to solve. We're trying to give solutions to this structure where we guarantee that not more than one process would be in the critical section. If that is satisfied, then we would have a solution to race conditions. Okay? That if someone is trying to change this shared resource, then let them do it fully. Even if they're stopped by the scheduler, So if a process is running in the critical section, it is stopped. Like, okay, some other process will run. But when that process starts running, it will not be allowed entry into the critical section. Because some other process, even if it is not running right now, is in the critical section. Let it come out. Only then this other process will be given entry. Are you able to understand this? This general idea? Okay.
Yes, sir.
Excuse me. Yeah. Just 1 second. Okay. So any solution to the critical section problem has to satisfy these three conditions. What is the first condition? The first condition is the most obvious one. Is that if there are so many of these processes, only one of them, maximum one of them, can be in their critical section. That's all. The second and third one might look very similar to each other, but they are not. Please pay some attention to what I'm saying right now. What is progress? If there is no process right now that is in its critical section, and some of them want to enter their critical section, then the decision to let one process know that they can enter cannot be postponed indefinitely. Okay? So the important thing is that if there is one process in the critical section, then that is fine. Progress is happening. I mean, the first condition for progress is not even satisfied, right? If no process is in the critical section, and if some processes want to enter the critical section, then that decision cannot take a very, very long amount of time, is what this is trying to say. Because if no process is in its critical section, some of them want to enter, but you're not able to take that decision, then you are hampering progress. But if one process is there in the critical section, then that's fine. It can take a very long amount of time. No one is telling it, oh, you have to finish in 2 seconds and come back. No, you can take 2 days inside. That's fine. But if no one is there, some of them want to enter, then take that decision quickly. Did you get that idea?
Yes, sir.
Okay.
Yes, sir.
Then we'll go to bounded waiting. Bounded waiting is very different from progress. Here this is saying that if I am a process, if I have asked for permission that I want to enter the critical section, but I am waiting for that decision, some other process comes after me, it gets the permission before me. Then okay, I'm waiting. Another process comes after me, that gets ahead of me in the queue. There should exist a bound, a limit to for how long that can happen. Okay. Other processes are allowed to enter after a process has made a request. Okay. So you cannot be made to wait indefinitely when you have already expressed your interest to enter the critical section. Can you see that bounded waiting is different from progress? It's like progress tells us is that if there is a room and you want to meet the principal is sitting inside the room. And if there are 10 students outside, no one is there inside the room. So the person standing outside cannot take a very long amount of time to decide who to allow to enter. That is progress. Bounded waiting is that when you were ahead of everybody, you came at 8 o'clock to meet the principal and someone was there inside. So the security guard said, okay, you cannot go. Someone is there. You have to wait. So you are waiting. Someone is there inside the critical section and they come out and they again stand in the queue. Now they are again given the chance to enter. You are still waiting. Other people come at 10 o'clock, someone comes at 11 o'clock, they are all given access, but you are still kept waiting. So there has to be a limit before you become really angry and say, what the hell is happening? I came at 8 o'clock, now it's like 6 o'clock in the evening and still I'm waiting. So there has to be a bound on that. Some bound has to be there. Is that making sense to all of you? The difference between progress and bounded waiting?
Yes, sir.
Yes, sir.
Okay. All right. So let's look at the Peterson's solution. So the Peterson solution is a classic solution to the critical section problem, a two-process critical section problem. Only two processes are there, P0 and P1. And they are trying to run at the same time and they employ two variables, the turn variable and the flag array. The flag array contains two Boolean values and the turn is a single integer value. They are both shared. Okay, these are both shared. So what does the turn variable contain? The turn variable says whose turn it is right now to be in the critical section. Okay, if two processes are there, process 0 and process 1. If turn is equal to 0, that means process 0 is in the critical section. If turn is 1, then it is the process 1 whose turn it is to be in the critical section. That is the turn variable. Then there is a flag array, which is kind of like flag. And there is the 0th location, there is this 1th location. If flag 0 is true, that means process P0 is interested to enter its critical section. If flag 1 is true, and both of them can be true at the same time, then process P1 is now interested in entering its critical section. This is just expressing interest, but turn can be either 0 or 1 because only one of them can be in the critical section. Is this clear? What is the meaning of these two variables and why they are being used here? Okay, let's look at the program. Okay, now you'll get a feel of what's going on. So if this is process Pi and the other process is process Pj, okay, keep that in mind. Process Pi's code is written like this. Let me do the correct thing here. So this is the code for P0 and this is the code for P1. So let's say P0 starts executing first. So P0 says that flag of 0 is true. What does this say? That I am interested in entering my critical section. Correct? True or false? Okay. So after expressing its own interest that I am ready to enter the critical section, it allows the other process to enter its critical section by setting the turn to 1. Like I am interested, but you run. Okay. Then it comes to the while condition. This while loop. Where, what does this read? This reads, if the other process, flag 1, is true, that means if the other process is interested in being in its critical section, and it is also its turn is equal to 1, then don't do anything. Just keep spinning inside this while loop. This while loop has nothing in it. It is terminated immediately. There is no block inside. Until this condition is true, just keep being inside this while loop. So what does this read again? If the other process is interested in running in its critical section and it is actually also running in its critical section, it is its turn, then don't do anything. Well, let's look at the other process. Let's just say it is running in its critical section. Okay, P1 is inside its critical section. That means what must be true? This entire thing must be true. Otherwise, this AND condition here. If this thing is true, that means both the left and right are true. Okay, that is the reason why P1 is inside its critical section. The moment P1 is done with its critical work, it's going to come out, it's going to then signal P0 by saying that, okay, I am now not interested in being in my critical section. So it sets its own flag value to false. What happens here in P0? This left part becomes false. That means process P1 is not interested in running in its critical section. And P0 enters its critical section because this condition for the while loop becomes false. Okay, so P0 is now in its critical section. Okay, let's just say it is running in its critical section. Let's focus on P1 right now. P1 runs its remainder section, then it comes back to the top where it again expresses interest that, okay, I am interested in running, but I'll give you the chance to run. So it sets the turn flag, the turn variable to 0. Then it runs this condition. Is the process P0 interested in running? Yes. It has done that at the beginning. Okay. And is it actually running in its critical section? Yes. Who set this variable turn to 0? This process only, P1. Is P0 running in its critical section? Yes, it was. We have actually left it inside its critical section. So now P1 is going to be spinning inside this while condition. It will not be able to enter the critical section until P0 is done. When P0 comes out, it sets its own flag to false, thus signaling P1 that it can continue and enter the critical section. And actually that is correct because this flag 0 would become false, this entire AND condition would become false, this while will not run anymore, P1 will be able to enter its critical section. Are you all able to see what's going on here? How they are maintaining this condition that only one process can be inside its critical section using these two shared variables, flag and turn?
Yes, sir.
Okay.
Yes, sir.
Okay. So we can prove, and this is where we will stop the class after this slide. We can prove that mutual exclusion is preserved. We saw that only one process can be inside the critical section. How is progress satisfied? Is progress satisfied? What is progress? If none of them are in their critical sections, and if one of them wants to enter, or both of them want to enter, then that decision cannot take a very long amount of time. Is that true? Let's just say both of them are in the remainder section, and one of them goes to the top. It can set its flag to true, then turn to the other thing, then come and run this thing, this condition. So process P1 has not gone to the top and it has not set the flag, its own flag to true, then P0 can immediately enter its critical section. Yes or no? It can. So that the decision was not, did not take a long amount of time. Who is taking the decision? This while condition itself. And it's not waiting indefinitely. Okay? And if P0 enters its critical section, then P1 cannot. But at one point, let's just say both of them are at the top, then this turn variable will have this one value at the end. Either it will be 1 or it will be 0. And that will dictate who will enter the critical section. Turn cannot be both 0 and 1 at the same time. Right? So progress is satisfied. Right? If none of them are there in the critical section, if one of them wants to enter, then that decision is not going to take a long amount of time. It will happen pretty quickly. Are you all able to see how that is the case here?
Yes,
Yes,
sir.
Okay. Then we have bounded waiting. What is bounded waiting? Bounded waiting is if P0 is waiting in this while loop. Why is it waiting in the while loop? Because, well, P1 is interested in running in its critical section and it is actually running in its critical section. That's why P0 is waiting. But the moment P1 gets done with its critical section, the moment it sets flag of 1 to false, saying that I am not interested in running in my critical section anymore, then P0 can actually enter the critical section. It is going to be rare that P0 is still in its while and P1 finished its critical section, got done with its remainder section, went back again and again entered its critical section while P0 is still spinning in the while loop. That should be rare, right? Right? P0 is still trying to run this condition, but P1 was in the critical section, came out and entered again without P0 getting a chance. Can it happen? Yes, no? Like P0 is waiting. Okay, let's discuss how does a while loop work first. Then we will go and proceed further in the class. The while loop runs. Why does a while loop run? What do you put here? You put a condition here. And the
So
while,
it will run until its condition is matched. Till its condition is matched.
yeah, so when the condition continues to remain true, it will keep running. So what happens if I do not put, a curly brace and write a statement? Can I write a while loop like this without any body? Don't get confused. There is a semicolon here. And this critical section is not a part of this while loop. Okay, this critical section is not a part of this while loop. This while loop does not have this as the body. The while loop is actually getting terminated here. So don't think that, this while loop, when this is true, then the critical section will run. No, it's actually the opposite. When this becomes false, only then this while loop will stop. And when this while loop stops, it will come to the next statement. This is a next statement. This has got nothing to do with the while loop. Okay, we'll discuss this in more details. I'll write a C program and show it to you. Okay, how this works, and then you will be able to understand it better. It's all right. These things can get confusing a little bit, but we will take it slow and we will do this in more details. Okay, so let's continue with the class. So I think in the last class we were studying about the Peterson solution. So let's take a quick look at that algorithm. So basically we had a flag array So if the two processes are P0 and P1, so the flag indices would be flag 0 and flag 1. If flag 0 is true, then P0 is showing intention that it is ready to enter its critical section. If flag 1 is true, that means process P1 is ready to enter its critical section, but they each give the other process the chance to run, and they check this condition, and the condition basically reads, if the other process is ready to run and it is its own turn to run, then it will wait, because then the other process is in its critical section. So you will have to wait in the while loop. I mean, the loop is basically just one line, right? It is just one line of code. You see, the critical section is not a part of this while loop. No, no, no. The critical section is not a part of this loop. This while loop is getting terminated right here. Since the while loop is getting terminated right at the semicolon, all this while loop does is checks this condition and stays in the same while statement when this condition is true. When this condition becomes false, it comes out of the while loop, goes into the critical section. Okay. Are you all able to see this? You'll be able to understand this if you have done your C programming properly. Okay. So there is a difference between these two things. By the way, can you see my screen and hear me?
Yes, sir.
Yes, sir.
Okay, cool.
Yes, sir.
So we were studying the Peterson solutions last time. Is that correct?
Yes, sir.
Okay, did we finish it completely, or were we kind of confused about the while loop?
No, sir. You said to explain again in the next class.
Oh yeah, I remember. Okay. That's exactly what we will do here. The problem is that, you know what's happening. There are 3 sections, and I'm actually confused sometimes what happened in the last class for each section. So if you give me a quick reminder, this is what was done, then it becomes easy for everybody. That's all. Okay. So if I do okay, so that printf statement is never going to get printed. Okay, so let me Control C, show you the code again. Look at this. Why did the printf never get executed?
In
Sir, it is stuck in the while loop.
At I slash.
Okay. All right. So, but if I just make a small change, now
it will print infinite.
correct. Okay. All right. That's the difference here. You're able to see that, right? It's this semicolon makes this while a separate statement of its own. The critical section, it is indented, but that is not, should not give you a false impression that it is part of this while loop. No. Okay. That's all I wanted to say. So until this, so let me explain this to you again. What I'll do is, This is for process P0. This is for process P1. Okay. P0 and P1. So what's going on in P0? It says that I am ready to run. That's why it is setting its own index in the flag array to true. Then it is letting the other process run first. So it is letting P1 run first. And this condition in the while loop basically reads like this. If the other process is ready to run and it is its own turn to run, then you get stuck in this while statement. You cannot come to the next statement. Okay? You cannot enter your critical section. Okay? So now that means P1 is running inside its critical section. The moment it is done in its critical section, it is going to come to this line of code in which it declares that it is no more interested in running its critical section. So it sets its own flag entry to false. The moment it does that, this thing here becomes false. This becomes false. And in an AND check, if one of them becomes false, the entire thing becomes false. So this while loop would not run anymore, and P0 would be able to enter its critical section. P1 is out of its critical section now. When P0 is running inside its critical section, if P1 is able to finish its remainder section, it goes to the top again. It sets its own flag to true, but it sets the turn to 0, which is basically signifying P0 here. Will it be able to enter the critical section while P0 is still in its critical section? Let's check. So flag 0, is it true? Yes. Flag 0 has been set true by P0 itself. And turn was set to 0 in the previous line. So this entire condition is true. So P1 will now be stuck in its while loop, will not be able to enter its critical section because P0 is in its critical section. Okay? So basically the Peterson solutions gives us mutual exclusion, that only one of them can be in their critical sections. The progress requirement is satisfied. What is the progress requirement? It basically tells us is that if no process is in its critical section, and if one or more than one of them want to enter their critical sections, then the decision process cannot be postponed indefinitely. Let's check. Let's just say both P1 and P0 are in their remainder sections. Can happen. No problem. No one is in its critical section. P0 wants to come in, set its flag to true, set the turn to 1, and then runs this check. It checks whether the other process is ready to run. But P1 is running in the remainder section. It has not yet set, this line has not run. So this condition here will be false because flag of 1 is going to be false. So P0 can immediately enter its critical section. So did not have to wait indefinitely to get the decision. Same thing can happen for P1 also. So progress is satisfied. Bounded waiting. What is bounded waiting? If you have asked for permission, then you cannot be made to wait at the permission line forever. There should be a limit as to how many number of processes can come after you, but they're given permission before you. For example, if P0 is stuck in the while loop, why is it stuck? Because both of these conditions are true. This flag of 1 is true and this turn is also equal to 1. That is why it is not able to go into the critical section. P1 is running in its critical section and P0 is continuously checking what's going on. It's not able to enter because this condition is always coming out to be true. The moment P1 comes out of its critical section, it sets its own flag to false. What's going to happen here? This condition will immediately become false and P0 will get a chance to enter its critical section. Look at this. So P0 is running its while loop, finding the condition to be true, not able to enter the critical section. Then it is stopped by the scheduler. P1 runs. It is running in the critical section. Okay. Then P0 runs, checks the while loop, condition comes out to be true, cannot enter the critical section. P1 runs again, it is able to come out of its critical section. So now it is running in the remainder section. Then somehow very quickly it comes to the top and it enters the critical section again. So when it enters the critical section again, all of these things that P0 was stuck on, flag of 1 would be true, turn would be still be equal to 1. Will it be equal to 1? Think about it. Will turn still be equal to 1? No. It will not be equal to 1. Because turn will be set to 0 by P1 itself. So, how can P1 enter its critical section? Can anyone take a look at this? I want you to look at the slide and think about it for a couple of minutes. And then I'll tell you what's going on. Maybe you will figure it out on your own. So P0 is running. It's not able to enter its critical section. Why? Because flag of 1 is true and the turn is equal to 1. That is basically trying to say that P1 is running in its critical section. Otherwise, what would this condition read in English? P1 is interested in running and it is P1's turn also. So P0 should not enter. And P1 is running in the critical section. P0 again makes a check. P1 is stopped in its critical section. That is fine. The scheduler can do whatever it wants. Maybe there is only one CPU core. Checks the while loop, figures out the condition is still true, not able to enter the critical section. P1 somehow comes out of its critical section, sets flag of 1 to false, goes to the remainder section. Okay. In the same step itself, in the same scheduler slot itself, it goes to the top, sets its own flag to true again. Okay. Sets the turn to 0. So the value of turn is 0. Basically, this is true. And flag of 0 is still true. Right? Because the flag of 0 has been set true by P0. And the turn was just set to 0 by P1. So can P1 enter the critical section again without giving P0 a chance? No, it cannot. Okay? It won't be able to. So that is how our bounded waiting is also satisfied. That if you have asked for permission, then you are the one who will get in. Basically, if P0 has asked for permission, it is stuck at the while loop. Then P1 is running in the critical section. Even if the scheduler gives it a lot of time, it won't be able to come out. It will be able to come out of its critical section, run through its remainder section, go to the top. The moment it goes to the top, it sets turn to 0. Basically, they are cooperating with each other. It's like, I have run once, why don't you run? I'm giving you a chance. That is the reason why they each set the turn to the other process at the top. P0 sets turn to 1 and P1 sets the turn to 0. It's because if the other process has been waiting in this while check, they will immediately get a chance to run. Is this kind of making sense to you?
Yes, sir.
Okay. Take a look at this. I am pretty sure that you will have some doubts. Even I get confused sometimes. So look at this. If you have any questions, you can discuss with your friends, or you can ask me also. Okay. Now let's go to synchronization hardware. It's like, as a programmer, you are not expected to write the code to protect your critical sections. Like, you are not expected to write Peterson's solution or whatnot. And everybody will come up with their own kind of solution. Some of it will be buggy, and locking is very critical for the correct functioning of your computer. If locking doesn't work properly, then things will get corrupted, because shared pieces of memory will be accessed by multiple processes incorrectly. They will corrupt the memory. The memory gets corrupted, then it's very difficult to keep continuing with the OS. You need to restart your computer. You have all seen that, the blue screen. So many things keep happening. You cannot trust the computer anymore. So since you are not expected to write your own locking solutions, it's the onus is then on the operating system developers and the hardware vendors, the processor makers, right? The people like Intel, AMD, the different architectures like ARM, whoever makes them, designs those architectures, it is on them to give us instructions which can help us with locking. So basically, if your critical section is right here, then you can always acquire a lock take care of your critical section, and then release the lock. Okay? You can acquire the lock. Once you have acquired the lock, any other process cannot get the same lock, because you have the lock with you. Then only you are allowed to enter the critical section. When you are in the critical section, you also have the lock with you, so no one else can do anything about it. They all have to wait here. Give us the lock, all of them, but they cannot get the lock because one of them has the lock. They are inside the critical section. When they are done, they will release the lock, and then one of them will get the lock. This general idea is what we're going to explore further in this chapter. But you could also ask me, I can tell me, Jyoti, that in uniprocessors, in which only a single processor is there, you could disable interrupts. Process P0 is running. It is stopped by the scheduler. Then process P1 runs. Then process P0. What do we mean by it is stopped by the scheduler? How does the scheduler even get a chance to run? Because the CPU is first interrupted by the timer interrupt. Otherwise, the CPU will not be able to run anything else. The CPU will continue to execute whatever it was running, which is process P0. How does the operating system code, that is the scheduler code, even get a chance to run? Because the timer interrupt interrupts the CPU. But if you disable the interrupt, if you disable all sorts of interrupts, then the CPU will basically run P0 completely. And then once P0 is done, maybe it will start running P1. So then if P0 ever enters its critical section, then it will not have the fear of it getting stopped in the middle while it was still working in the critical section. And P1 also trying to access the same memory. That opportunity will not arise if interrupts are stopped. We are worried about concurrent execution, and concurrent execution happens when two or more processes, they run kind of back to back without ever finishing what they are doing. And that is only possible if interrupts are enabled. If interrupts are disabled, then concurrent execution cannot happen. And if there is no concurrent execution, then the critical section problem is solved. Are you able to convince yourself this?
Yes, sir.
Okay. But what is the problem with disabling interrupts? It's like the currently executing code would execute without preemption. No one can remove it. It will execute until it is over. But it is too inefficient, right? The operating system should be too laggy. It's like they will not feel responsive. A process is running for a long time and then no other processes are getting a chance to run in the meanwhile, or nobody will use that OS. For performance and scalability, to be able to run thousands of processes at the same time, all of them should at least get this illusion that, okay, from time to time, we are getting a chance to run on the CPU. If they're waiting for too long in the ready queue, it will become very visible to the user that something is wrong with the system. I'm just trying to type something, move the mouse. See, if you move the mouse, so many interrupts are created. If you type something on the keyboard, for every key press, an interrupt is created. If interrupts are disabled, then what will happen to these mouse movements? So if you try to move the mouse, it will not move for a while, then immediately will jump somewhere. Then again, you cannot use the system that way. So this might be a solution, but this is not used anywhere. Disabling the interrupts is very, very rare in modern operating systems. So another topic that we want to discuss is atomic operations. What are atomic operations? So before we studied that if there is a counter variable, if you want to do C++, increment the counter by 1, then what would you have to do? You'd have to copy the value of the counter to a register. Then you have to do register equal to register plus 1. Then the value of the register will have to be copied back to the counter. 3 steps. 1, 2, 3. This is not atomic. Basically, the process can be stopped here, right? And the process will have to be paused midway. This is not atomic. Atomic operations are the ones which, when they begin, they cannot be interrupted. They will have to finish. Those are atomic operations. Okay. So software cannot provide that. Software runs line by line, instruction by instruction. Software can be interrupted anywhere by interrupts. So basically, it is the hardware makers, the architecture people, who'd have to give us instructions, certain instructions, which do a little bit more than simpler instructions. They are supposed to be a little bit more complicated because they can do things like increment something or set a memory to a certain value. All of that can be done in just one step and no one can interrupt while that instruction is happening. Interrupts usually happen after an instruction is executed, right? You execute one instruction 0. It's like you're dividing 2 large numbers. This is taking a lot of CPU cycles. Interrupts cannot interrupt that. No, interrupts can happen before that, interrupt can happen after that. But while this instruction is executing, it cannot be interrupted. Processors are, when you will study this in your architecture course very soon, that interrupts cannot stop an instruction. They will have to wait for the instruction to be over. So if we take this entire thing of copying something from memory to a register, incrementing the register, then copying it back to memory into one instruction, instead of like 3 instructions like this, then this cannot be interrupted. And this can help us solve our critical section problem. We will see how that is done. Okay, let's look at the test and set instruction. Okay, so the test and set instruction code is given here. This is just like the algorithm. Excuse me. This is just like the algorithm for the test and set instruction. There is no C code for the instruction. The instruction is made in silicon on hardware. This is just given so that you can understand it properly. Okay. Otherwise, you can tell me that, Jyoti, this is again some 3-4 steps. I mean, the process can be stopped here. Then how is this atomic? How can this be executed in one step without any interruption? Well, this is just the algorithm given for your understanding of how this instruction works. Otherwise, this is just implemented as one atomic instruction in the CPU. One atomic instruction. Okay. Once it starts executing, it cannot be stopped. So, what does this test and set instruction do? It takes a pointer, it takes the memory address of a target. It then stores the value of this target into a returned value. Okay. Then it sets the target to true. It returns the old value. So whatever the value of the target is to begin with is captured in this return value. The target is compulsorily set to true, and then you will get the old value of the target, the original value when you started with this instruction. Okay, is this clear to everybody? These three steps. We will see how this is used later. Is this clear? Are you able to understand what is happening here? Take the
Yes,
target.
sir.
Okay,
Yes.
okay. So take the target, capture its old value. It could be false, it could be true, whatever. But always set it to true and then return the old value. Okay, let's see how this can be used as a lock. Okay, how this can be used as a lock to solve the critical section problem. Okay, so we have a lock which is a Boolean variable. It's just a Boolean variable. Its address is what we pass because this test and set instruction takes the address of that lock. So we pass the address into the test and set. Okay, so to make this clearer, let me kind of make a copy. Okay, current slide. All right, so let's say this is P0 and this is P1. Okay, and there is a shared lock variable. This lock variable is a Boolean variable and which is shared. So let's assume the lock is initially set to false. Okay, and P0 is the first one to execute the test and set. The test and set instruction is atomic. Also, it is an exclusive instruction. That means that first of all, it is atomic. That means that when the test and set is executing, this process cannot be stopped. Okay, so the banking kind of problem cannot happen with this lock variable. This lock variable will not result or will not end up, being treated like the bank balance variable in which you read it, you update it, but before you can write it back to memory, somebody stops you. No, that situation will not arise. Okay, because here getting the value, setting the value, and returning the value, all of them happen in one shot, one atomic operation. Okay, that is there. Also, this instruction gives you the guarantee that if you are working on this lock variable, this particular lock variable, then another process like P1 will not be allowed to run test and set on the same lock variable. On the same lock variable, you cannot run test and set until the other process is done with test and set. So basically, it can go something like this. On the CPU, you can have the test and set instruction on lock 0 maybe. But while this is running, another process on another CPU, okay, let's just assume there are two CPU cores, cannot run test and set on the same lock parallelly. If there is one CPU, then it cannot happen for sure because you are running test and set on lock 0. But until you are done with this instruction, nobody can stop you. So forget about another process running test and set at the same time. Cannot happen. On a single CPU, it cannot happen. But I'm telling you that even on multiple CPUs, on the same lock, two processes cannot be running test and set instruction parallelly. But this can do it on a separate lock. If it is lock 1, then that is possible. On the same lock, two processes cannot be running test and set at the same time. Is this idea clear to you?
Yes, sir.
Okay, so they have to be atomic. Once they start, they will have to end. They cannot be stopped by any interrupt. Also, they are kind of exclusive for a particular lock, not exclusive globally. It is like I'm running test and set, so nobody can run test and set. No, they can run on different locks, not on the same lock. That's all I'm trying to say here. Okay. So what's going on over here? Okay, let me go back again. Okay, here. So lock is set to false. Since the lock is set to false, P0 runs test and set. And while P0 is running test and set, if P1 comes and tries to run test and set on the same lock, maybe on a different CPU, then it won't be able to run that. It'll have to wait until P0 is done with running test and set. So test and set keeps the old value of lock, sets the value of lock to true, returns the old value. So here you're going to get a false. The old value of lock is false. False is returned, but lock is set to true. So since P0 gets a false out of test and set, its while loop is not going to run even once. There's a semicolon. So it's going to come into the critical section. So P0 is now in the critical section. What happens to P1? Since P0 is out of test and set execution, P1 can run test and set. It gets the old value of lock, which is now true. So it gets true. It also sets it to true. So no change in the value of lock. But if it gets a true, then it will not be able to come out of the while loop. It will be stuck. So P0 runs the critical section, comes out, sets lock to false. The moment it sets lock to false, P1 is continuously executing test and set inside the while loop, that single line while loop. Now it is going to get a false because P0 sets the lock to false. It's going to get a false. It will then set the lock variable to true. It will return the false out of the while thing and it will come out of the while, enter the critical section. Lock is now set to true. By whom? By P1. So now P0 cannot enter. It is going to get a true all the time. Okay, is this clear to everybody?
Yes, sir.
Okay, all right. There is another very similar instruction which we will quickly discuss and then I'll let you go. So compare and swap instruction, another atomic exclusive instruction, compare and swap. So it takes the pointer of an integer variable, then also takes an expected value and a new value. All it does is it keeps the old value, then subsequently returns it to you. But if the old value is equal to the expected value, only then the value is set to the new value. Okay. So it gives you the old value, but if the old value is equal to the expected value, then the new value is put into the value. That's all it does. So this is also very similar to test and set, right? Test and set basically always sets the value to true. Here you set the value to the new value, and also test and set works on Boolean variable. This works on an integer variable, internal variable, that value thing here. This internal, whatever you call it, a lock or whatever, these are integers. In test and set, though, that is a Boolean variable. There you always set it to true. Here you set it to not to true. You set it to the new value. Whatever they have given as the new value, that will be set only if the old value is equal to the expected value. Otherwise, it will be left at its old value. Okay, is this clear?
Yes, sir.
Okay, correct. So let's look at this, how you can do locking here. Okay, I'll quickly look at this and I'll let you go. We will look at mutex and semaphores in the next class. I mean, we will finish this chapter in about 2 more classes. So next week, by the middle of the week, we will be done with this chapter. Then we will look at some old stuff that we might have missed out since the beginning of the class, like a few things, like 1 or 2 classes. Then we will be good to go for the exam. We have 20-25 days more for the exams. We'll practice problems and be really ready to do really well and understand OS properly as much as we can. All right, let's look at this. Compare and swap, lock. So the lock variable, let's just say the lock variable is set to 0. That's what it is written here. It's an integer variable, not a binary anymore, not a boolean. So its lock is set to 0. So when P0 runs this line of code, it basically gives the address of the lock variable. The expected value is 0 and the new value is 1. So what is going to be returned out of compare and swap? The old value of lock, which is 0. So 0 is going to be returned out of this. But will the value of lock be set to the new value? Yes. The old value is equal to the expected value. So the new value will become 1. So now lock has become 1. But 0 will be returned out of the compare and swap instruction. Is 0 not equal to 0? False. 0 is equal to 0. So this while loop will not run. It will be able to enter its critical section. But lock is set to 1. So if any other process comes and runs a very similar piece of code, what is it going to get out of compare and swap? A 1 will be returned there. Will it be able to set its value to anything? No. Its expected value will be 0, but the value is currently 1. There is no need to set anything anymore. Lock will remain at 1. And compare and swap will keep on returning its existing value, which is 1. So that process will not be able to come out of that while check. Because 1 is not equal to 0. True. 1 is not equal to 0. So that process will not be able to enter its critical section. But if this process, which is already in its critical section, if that comes and sets lock to 0, then the other process, which is continuously spinning inside this while check, will get a 0. And also, its expected value will match the lock's value. It will set it to 1 and it will be able to enter the critical section. Are you able to see what's going on? We finished talking about a couple of these instructions, the test and set instruction. And we saw how this instruction can be used to solve the critical section problem. We saw the compare and swap instruction, how that can be used to solve the same problem. Then the thing here is that hardware makers give you instructions like test and set, compare and swap. So you should not be using those instructions as application programmers directly, because there's a very good chance that either you or someone else, millions of application programmers, someone will make a mistake while using this. Any mistake that you do, like you set this 0 to 1 or whatever, don't use the correct operator, will make this instruction not work properly. And if you do not grab a lock properly, then multiple processes run a risk of entering the critical section at the same time, and then the entire effort is wasted. Alright, so the hardware makers give us these instructions. Then the system programmers, people who write operating systems, C libraries, various other core level software, they use these instructions to give us APIs or functions like acquire and release. Okay, and we as application programmers can use these functions to write programs. For example, we can use mutex locks. Mutex stands for mutual exclusion, right? So very simple to use. So if you are writing a critical section problem solution, then you can do something like acquire and give the address to a lock variable, a boolean variable, write your critical section code here, and then release the lock. Okay, so the first process coming in will be able to grab the lock, execute the critical section code while it has still the lock with it. Other processes will not be able to grab the lock until this process, the first process, releases the lock. Okay, and as I told you, acquire and release, all of these functions are implemented using atomic instructions, the kind of instructions we looked at in the last class: test and set, compare and swap, and things like that. So when the first process gets in and is able to run the critical section code, what happens to the rest of the processes which are not able to get in? They are stuck in a process called as busy waiting. So all of them are in the running state process wise, but they do not go to the waiting state. From time to time they go to the ready state because the scheduler will put them in that state, and they come back to the running state again if the scheduler wishes. But they're all stuck in the same place. They're not able to go into the critical section because another process is running in its critical section. That is called as busy waiting. Let's see how that looks like. In very simple terms, it's kind of like this. And while the lock is not available, keep spinning inside the while statement here. Don't go beyond this line. But the moment the lock becomes available, then you make the lock unavailable for the rest of the people and you run the critical section code here. When you are done running the critical section code, you set available to true so that someone else who is stuck in this while statement will be able to enter the critical section. Something like this: acquire the lock, run the critical section, and then release the lock. Right? So this is why it is called as a spin lock, because one process can enter, the rest of them will be stuck in this while. They are in the running state, they do not go to the waiting state. Okay, is this making sense to everybody? The idea of mutexes?
Yes, sir.
Yes, sir.
Okay. Let's look at semaphores. Now, mutexes are very simple. They're kind of these binaries, right? One process can grab the lock, the rest are not allowed to grab it while someone else has it. But let's look at something which is different than mutexes. Well, not entirely. If we're talking about semaphores, a semaphore is a very simple concept. It is just an integer variable which supports these two operations on it: the wait operation and the signal operation. And keep in mind that the wait can also be called as P, signal can also be called as V. In the exams, they like to use P and V. So always remember that wait is the same thing as P and signal is the same thing as V. Okay? What they do is, if S is an integer variable, any process executing the wait operation, and by the way, wait and signal are atomic operations, just like acquire and release. They're atomic. Once they start running, they end without that process getting preempted or stopped in between. And when one process is running a wait operation on a particular semaphore, S, then no other process can be running wait or release, so wait or signal, on that same semaphore. Just like we saw in the test and set, for a particular lock, only one process in the entire system can be running test and set on that particular lock. They can run test and set simultaneously on other locks, but on the same lock, only one of them can be running. Same thing applies here. Okay? But the wait operation is very simple. The value of the integer is not positive. just like it's less than equal to 0, then you busy wait. Keep spinning in the while statement. Don't go further. You are stuck. But if the value is positive, then you decrement the value and continue. When you are done, you signal. Signal is very simple. You just increment the value. Okay? So think of it as a ticket, right? So there is one ticket on the table. In the room, there is nobody. You can grab the ticket. So the ticket value would now go from 1 to 0. So you do a wait, you decrement the value, get inside the room. Any other processes coming in, if they do a wait on the integer variable s, then they cannot, because the value is now less than or equal to 0. Precisely it's equal to 0 right now. That means there are no tickets on the table. They cannot grab a ticket. Grabbing a ticket is like s minus minus. They cannot do that. So they're stuck in the while loop. The person in the room, when they come out, they do signal. That means they put the ticket back on the table. That's s plus plus. Then the person who is waiting in the while loop will find s not to be less than equal to 0. S is greater than 0 now. Its value is 1. Then they can do s minus minus and enter the room. Is that idea making sense to you?
Yes, sir.
Okay. So that is a binary semaphore. What I talked about is a binary semaphore. So if S can only take on values 0 and 1. If it is 1, someone can wait and make it 0, and someone can signal and make it 1. This is a binary semaphore. Then there are also counting semaphores. Their values can be more than 1. Like the value can be 5, for example. 5, 4, 3, 2, 1, 0. All of these values this integer can take. When is this useful? Like there is a room and there is a table outside on which there are 5 tickets. And a person comes, grabs one ticket, enters the room. Another person comes, grabs another ticket, enters the room. How many tickets are there? 3. Goes. This person goes, this person goes. Okay? 5 people are there in the room right now. And there are 0 tickets on the table. 6th person coming in, when it does a wait on S, it's going to be stuck in the while loop because S is now equal to 0. There are no tickets, cannot do S minus minus. So what this counting semaphore can be used to kind of let only maximum 5 people into the room. When a person comes out, they put the ticket back on the table, the S becomes 1, number of ticket is 1, then this 6th guy can enter. Is that making sense to you?
Yes, sir.
Binary semaphore 0, 1, kind of like a mutex, acquire, release, on, off, but counting can be more than 1. It can count and just can do up to a certain number. Exactly what I was telling you, right? Counting semaphore, binary semaphore. It's like 0 and 1, mostly like the mutex locks, acquire, release. You can solve various synchronization problems. For example, look at this simple problem here. If P1 and P2 are 2 processes and they require S1 to happen before S2 under any circumstance, then you can create a semaphore called sync, initialize its value to 0. Sync is an integer variable, right? Initialize its variable to 0. So let's just say P2 runs before P1, worst case. What can happen? P2 first waits on sync. Since the value is 0, it cannot go any further because sync is less than equal to 0. Sync minus minus cannot be done. So this is going to be stuck in the while statement. After some time, the scheduler stops P2, runs P1. P1 immediately executes S1, the operation S1. So now S1 happens before S2 because S2 cannot run. P2 is stuck in this. Then P1 signals sync. Like the value of sync is now 1. Then if P2 runs, then this wait can move to S2. It can do sync minus minus because sync is no more less than equal to 0. It is greater than 0 right now. This is how you can enforce that S1 always occurs before S2. Can you see this?
Yes, sir.
Okay. All right. So there are two kinds of semaphore implementations. One uses busy waiting. I mean, whenever you see busy waiting, mostly think of a while loop which runs until a certain condition is false, and then it will move further. Otherwise, it is going to be in the while statement, heating up the CPU, staying in the running state, but doing nothing useful. It should rather go to the waiting state. The 5-state process model which we saw: new, ready, running, waiting, terminated. So processes in the waiting state, they're not active. They're waiting for some disk input output or some input output. They're waiting for that to happen. Similarly, if you have a semaphore and you are not able to do S minus minus, you cannot get through the wait operation completely, then ideally you should not be stuck in the while loop, because the processor, the CPU is still running you continuously in the while loop while you are still not able to progress. Okay, so well, let's look at that version first. We have looked at that version here, right? Until it is less than equal to 0, be in this while loop continuously, be in the running state, go to the ready state sometimes, but when you come back to the CPU, you are still stuck in the while loop. This is the busy wait version of semaphores. Now, the good thing about these kinds of semaphore implementations is that they are very simple, right? Few lines of code, and you can do whatever you are doing. And they are only okay if the critical section is small. Like you do wait on a particular semaphore, do the critical section, and then do signal. If the critical section is small in size, then when a process comes, it is quickly able to execute critical section, signal it back, and go. If another process comes during that, and the amount of duration it spends waiting in the while loop is very less, so it's acceptable. It's also acceptable if the critical section is a rarely executed. So first of all, it is okay if it is small. It is also okay if this is rare. Like, no one wants to run the critical section. Very rarely a process would want to run in the critical section. So then it is very likely that whenever someone comes and runs the wait, it is actually able to get the semaphore because it is rarely occupied, right? So then very rarely would somebody would have to be in the while loop stuck, because it is not very famous. The critical section is very rarely run. In those situations, busy waiting is fine. But in other situations, we can implement semaphores using blocks and wake ups. Well, let's look at this structure. Instead of this semaphore being just a single integer variable, we also have, we put together the integer and the list in one structure. What is this list? Well, let's take a look at this. Now, these are implementations of semaphores without any busy waiting. As you see, there are no while loops. So when a process waits on a semaphore, so this semaphore is now a structure, right? As we saw in the previous slide. And we pass a pointer to that structure. So immediately what we do, we decrement the value. Okay. If the value is less than 0, no less than equal to, because in the other implementation we did S minus minus after the while loop. But here the decrement has already been done before. So if the beginning value of the semaphore is 0, now it has actually become -1. Okay? It should not allow even this process from entering, because no tickets on the table already. You made it -1, even you cannot enter. Okay? If it is 1 to begin with, you make it 0, then it is fine. One ticket was there, you grabbed it, you go. No need to wait. You can go forward and do your critical section. But if you made it negative by running this line, then you cannot go any further, right? This process will be added to that list, okay? This list here, this list. And block will be called. What will block do? Block will take the process from the running state and put it in the waiting state. The process is waiting in this list, okay? And whenever a process is done working in the critical section, it will signal the semaphore. It will take the pointer, pass it. It had decreased the value, right? Now it will increase the value. If the value is less than equal to 0, that means there are one or more processes waiting on that semaphore in the list. Okay, wake them up. So what's going on here? Well, let's see. Let's say the value of the semaphore is 1. When the first process enters, it makes it 0 and it is able to enter the critical section. The second process that comes makes the value -1. It is waiting in the list. Third process makes it -1 to -2. This also waiting in the list. Cannot. Now, when the only process in the critical section is trying to come out, it will take the value and increment. So -2 will become -1. Okay? But this -1 signifies that 2 processes are waiting in the list. That is why the less than equal to symbol is used here. It should wake up one process, at least one process from the, so that process is woken up. The process goes from waiting to the ready state. And then it can go to the running state if it is scheduled by the scheduler. Since that process has already done minus minus, it was actually blocked here, it can actually continue immediately and enter the critical section. Okay, are you able to understand what's going on here?
Excuse me, sir.
Yes,
So can you please explain again the process of -2 to -1?
yes. So let's just say we can take the initial value to whatever number. Let's just say the initial value was 2 in the semaphore. That is very clear that 2 processes can enter the critical section or a room or whatever. 2 tickets are there. When the first process comes, it does value minus minus, makes the value 1, enters the room. Second process comes, value is 1, makes it 0, enters the room. So 2 tickets are gone. Is this clear until now?
Yes, sir.
Okay. Now when the third process comes, it makes the value -1 immediately by running this line. And since its value is less than 0, it has to wait in the list. So it goes to the list. Okay. Maybe another process comes, takes the value from -1 to -2, still less than 0, goes to the list, cannot enter the room. Now maybe one of these processes which are inside the room, they are done. Now they want to signal. So they immediately increment the value. So the value now goes from -2 to -1. But now it is their responsibility, since they are coming out, they should wake up another process, right? And tell them that, okay, get out, come out of your sleeping state, your waiting state. You can enter now. Because, 2 tickets were there. I am putting my ticket back. So whoever was waiting for that one ticket can get up and enter the room. Is that idea making sense?
Yes, sir.
So now, okay. So now, why will it wake it up? Because its value is -1. Okay, it is still less than equal to 0. So the less than equal to 0 basically signifies that one or more than one processes, they are waiting in the list. Okay, so now this process will end, but this first waiting process, right? This will now enter the room. Now there are 2 processes in the room again. Okay. It goes on like that. Like when another process comes out, they will take the value from -1 to 0. Since it is less than equal to 0, that means another process is in the list, which is basically this. Okay. Now that process will then enter the room. Now there are two processes in the room. The value is 0. But is there anyone in the list now?
No, sir.
No. So when the two processes in the room they come out, the first process will make the value from 0 to 1, which is not less than equal to 0. It is greater than 0. So then this code will not be run. Nobody will be woken up because nobody is waiting in the list anymore. And when the second process comes out, it will take the value 1, make it 2 and enter and get out. So now the number of tickets on the table have become 2 again. Okay, made sense?
Yes, sir.
Okay. So let's see how when you use semaphores incorrectly, it can result in deadlock and starvation. If S and Q are two semaphores, and if P0 and P1 are coded up like this, if P0 waits on S, makes the value of S 0, P1 waits on Q, makes the value of Q 0. Now P0 wants to wait on Q, cannot go any further, value is already 0 by this line. And P1 waits on S, S's value is 0 by this line. They're both stuck. This wants the value of Q, which is grabbed by this, and this wants semaphore S, which is grabbed by this. They're both waiting on each other now. No one can proceed. Can you see that?
Yes, sir.
Okay. This can lead to starvation and indefinite blocking. If you use semaphores incorrectly, then these kinds of things can happen. Let's start looking at these three classical problems of synchronization. We will solve these two using semaphores. This one we will solve using semaphores. We will see how a deadlock can happen. Then we will try to solve this using a concept of monitors. And this will have no deadlock. Okay, so let's start looking at the bounded buffer problem. Maybe I will try to finish these two in this class. This one can be finished in the next class and we will be done with our syllabus almost for the midsem, and we can start practicing and start looking at few things. The midsem is like almost a month away from now. We've got a lot of time to practice and look at some basic things which we might have skipped the previous classes, right? Okay. The bounded buffer problem is something that we had discussed before during the start of this class. We had the counter variable, in-out variable. We saw how the counter variable, when it was shared by the producer and consumer, was leading to inconsistencies, right? So let's revisit that problem. So there is a buffer, okay, and whose size is n. So n buffers, so n is equal to 5. 5 buffers are there. We will use a mutex. I will tell you why this is used when we will look at the code. Its initial value is 1. Then there is a counting semaphore called as full, initialized to 0. This basically signifies how many buffers are filled up. Currently, 0 buffers are filled up. Semaphore empty, initialized to n. Why? Empty signifies how many buffers are empty. And since all the buffers are empty, its value is n. So if you do everything correctly, the sum of full and empty should be equal to n. The number of empty buffers plus the number of filled up buffers should be equal to n. Correct? Okay. Let's proceed and look at the producer. What does the producer do? The producer produces an item, right? It has to run some code to make that item, whatever it's trying to make. Then it is going to wait on empty. So empty is equal to 5, full equal to 0, n is equal to 5. 5 buffers are there for this particular example. Why does the producer wait on empty? It's because if the value of empty is 0 or less than 0, that means there are no empty slots. If there are no empty slots, then the producer cannot put that item anywhere. So it will wait on empty. So since empty is 5, everything is empty. 5 will become 4 right now because of this wait operation. there is a mutex binary semaphore whose value is 1. This wait mutex will make this 1 as 0. Then the producer will add the item to the array. After adding the item to the buffer, it will signal mutex. Mutex becomes 1 again. It will not signal empty, it will signal full. Why? Because now there is one filled up value, full will become 1. Again, you see 4 plus 1 is 5. Can all of you see this? So you wait on empty. So you wait until you find an empty slot. Then you wait on mutex. Why you wait on the mutex? Because you are trying to change the buffer. I will show you a situation in which if this is not there, the producer and consumer can again start tinkering with that array simultaneously, which is what we don't want. Because even if the buffer is there, here, there's a buffer. But there might be some variable, maybe the location variable, which says, okay, these two are filled up. The producer should put the value next into this. So these kinds of variables can be internal to the array. If both the producer and consumer are again working on this, they will mess this value up, just like the counter variable. We don't want that. Okay, that's why anytime you're trying to change the values inside the buffer, it's best to kind of grab a mutex, a binary semaphore, work on the buffer and then signal it. Okay, but the way the producer is unique here is that it waits on empty. Basically, it takes an empty ticket, takes a buffer. Now the number of empty is 4. But then it signals full, because now one buffer is filled up. What does the consumer do? It waits on full. Why? Because if the value of full is 0 or less than 0, that means nothing is filled up. Everything is empty. It cannot proceed. What will it consume? Okay, and that is why the producer signaled full. So I have filled up one value. It's telling the consumer, you might be waiting on full. Since it is 0, you're not probably able to proceed. But now that I've made it 1, something is available, you can continue. Okay. Now this will, because it is going to remove something from the buffer, it will wait on this mutex, remove the item from the buffer, signal it, then signal empty. Why? Because now full was 1 to begin with, empty was 4. Now it waited on full, so it made full 0. It consumed the item. That means empty should become 5 again. Total is again 5, right? Because one item has become empty. Okay, you're all able to understand this?
Yes, sir.
Okay. Okay, now let's see if these mutexes were not there. What would happen? If I remove these mutexes and take a situation like empty equal to 3 and full equal to 2. Okay, 3 slots are empty, 2 slots are filled up. The producer comes, waits on empty, makes empty 2, and then immediately starts producing and putting that item into the buffer. Okay, let's come here. Now this also runs at the same time. Empty equal to 2, full is also equal to 2. Empty is 2 because the producer has changed 3 to 2. Waits on full, makes this full 1, enters and starts consuming something from the buffer. At the same time, the producer is also working on the buffer. Can you both see? Can you see that? They're not stuck at the wait call at the top. They're both able to start working on the buffer at the same time, which is, we don't want that. That is why this mutex call is needed. If the producer is using the buffer right now, then the consumer, even if it gets past this wait, even if it can go beyond this wait, it will be stuck here until the buffer has signaled the mutex. This consumer should not go and change the buffer, and vice versa. Okay, is it clear?
Yes, sir.
Okay. All right. So now let's look at this problem, and after this we will end the class. Okay. Very simple problem. What this problem is saying is that maybe there is a piece of paper, okay, and something is written on that. More than one or more than one readers can read this document. When the readers are reading this document, a writer cannot go and write. All the readers will have to get out of the document. All the readers, nobody is reading it. Then a writer can go, only single writer. Not more than one writer can be writing at any one point of time. You don't want 10 people to be writing on a piece of paper. Then the writer can go and make changes. When the writer is writing, a reader cannot read. Once the writer is done writing, then one or more than one readers can again come and read. Can you understand the problem? One or more than one readers can read. When they are reading, a writer cannot write. But once they're all gone, a writer can start writing. When the writer is writing, the readers cannot read. Once the writer is done writing, the readers can again start reading. Did that make sense?
Yes, sir.
Okay.
Yes, sir.
Let's see how to solve the problem. The data set is basically that piece of paper. This is the read-write mutex. Why is this used? Anytime you are reading or you are writing from the paper, you will need this mutex. This will kind of give you mutual exclusion between the writer and the group of readers. So there is a writer and there are some readers. They form a mutual exclusion set. Like when the writer is writing, these guys cannot be there. When these guys are there, the writer cannot be there. So this is a read-write mutex. Binary semaphore, if the writer has it, then these guys will be stuck. If these guys have it, then the writer will be stuck. It cannot write. Okay? Okay. Then we have a mutex. We will see how this is used. It's also a binary semaphore. Then we have an integer. It's not a counting semaphore, just an integer. Read count initialized to 0. Okay, let's see the writer process. The writer process is very simple. Okay, it is a reader processes where the things get slightly complicated, but it's also easy to understand. Okay, what happens in the writer process? The writer waits on the read-write mutex. Maybe the mutex is grabbed, the binary semaphore is grabbed by the bunch of readers. The writer cannot write. Once they release it, once they signal that mutex, then this writer will be able to enter, write, signal, and come out. Clear to everybody?
Yes, sir.
Okay. Okay. What about the readers? For the readers, it becomes a little bit complicated, but not very complicated. Look at this. When the first read, now let's assume there are no readers. The first reader comes, waits on the mutex, not the read-write mutex, the only simple plain mutex. Okay, now the value of the mutex is, it was 1, now it has become 0. Read count, it increments the read count. Read count was 0, now it has become 1 because it is the first reader. Then if you happen to be the first reader, 1 second. Okay, if you are the first reader, only then the read count will be equal to 1. Only the first reader is supposed to grab the read-write mutex. Because I told you, one or more than one readers can be reading. It is not necessary for all the readers to grab the read-write mutex. Only the first reader should be able to do that, and that will prevent the writer from writing when there is at least one reader. Are you able to understand this concept?
Yes, sir.
Okay. The moment this mutex is grabbed, read-write mutex, the writer will be stopped from writing, which is what we want. Then this first reader will signal. Okay, let me just index this properly. So what's happening here? If you are the first reader, then you do this. You grab the mutex. Then you signal the mutex variable. Now you probably have seen that this mutex variable is used to guard the read count. Now, when one reader is incrementing read count from 0 to 1, we do not want another reader to be doing the same thing. So we will do them one after the other. We do not want the banking example problem to happen or the counter problem to happen. Okay, so when one reader is incrementing the read count from 0 to 1 or from whatever value to the next value, it should be that only process which is doing it. The rest of the processes need to wait until that reader has done this brief piece of code, right? Incrementing read count, and the first reader will do this, but the rest of the readers will just increment read count and come out. So this mutex is only to guard this variable, which is also shared by all the readers. Are you able to understand why that mutex is used? Look at the code, you will be able to understand. Can someone tell me what if I remove that mutex, what will happen? If I remove these two lines, then what will happen? And two readers are coming in at the same time. What can happen? Reader 0, reader 1. Read count is 0. Reader 0 reads read count as 0 into the temporary variable, sets the temporary variable to 1. Before it can write it back, reader 1 also reads read count as 0, sets temporary variable to 0. Now both of them get set to 1. Now reader 0 sets read count to 1. Reader 1 also sets read count to 1. Two readers are there. Should read count be 1 or should it be 2?
2, sir.
Yes. I mean, this is the same problem which I kind of taught you in the beginning of the class, right? This, you remember this? Okay. Anyway, so anytime you are trying to update a variable which is shared by, I mean, this is exactly why we are studying the center chapter in the first place, right? You have a read count variable which is shared by so many people. If you're trying to update it, you have to take a lock and release the lock, right? I mean, is this not the entire critical section problem, guys?
Yes, sir.
Okay. All right. So let's continue with the discussion of the readers writers problem where we stopped last class. The story was like that. Like multiple readers can read the document, and when they are reading, no writer can write. When all of them are done reading, then a single writer can start writing. And when the writer is writing, no readers can read. Right? So this is how we tried to solve the problem. We saw this code for the writer where they just a single writer waits for the read write mutex, and this is a binary semaphore that is used to either let one or more readers into the document or just one writer into the document. Either a bunch of people can read or just one person can write. That's all. While they are reading, this person cannot write, so it waits for that mutex. If the mutex value is 0, that means the readers are reading, the writer won't be able to write. Once they signal, the value becomes 1, and then the single writer, which is waiting on this statement, would now then be able to enter right into the document and signal and set the value back to 1 again. In the readers, what happens is that there is a read count variable, which basically keeps count of the number of readers currently reading the document. Okay, we use this variable basically to find out who is the first reader and who is the last reader to exit. So who is the first reader to enter and who is the last reader to exit. Okay, and why do we need to know the first reader to enter and last reader to exit? Because the first reader to enter needs to grab the read write mutex, and the last reader to exit has to release that lock, has to signal the read write mutex. Otherwise, the writer won't be able to write. And there is only one mutex, so each reader need not have to grab this mutex. No, only the first one will grab and the last one will release. The rest of the readers can come in freely once the first one has grabbed that mutex. That is why we use the read count variable. And since the read count is a shared variable, multiple readers can do this read count plus plus and read count minus minus. So anytime we do read count plus plus, read count minus minus, we basically guard it by this mutex. This wait on mutex sigma. There is basically to guard this variable, the read count variable, so that only one reader can be incrementing or decrementing this variable. If multiple readers are doing that, then race conditions can happen. The same kind of a situation that happened in the banking example or the counter-based producer-consumer problem, which we studied in the first class, right? Those things can happen, and we don't want that to happen. So anytime there is a shared variable which can get updated simultaneously or concurrently by two or more processes, then you need to put a couple of locking mechanisms, right? Grab a lock or a semaphore, release the lock, and then let other processes change that value. Is that clear to everybody?
Yes, sir.
Okay. All right. So the first reader then comes, waits for the mutex, right? Because it is a first reader, then it is pretty much sure that the mutex's value is 1 and it can actually make its value 0. Enter this line. Read count is 0. It makes read count 1. And actually read count is equal to 1. This condition will be satisfied, and that first reader will also try to grab the read write mutex. Now the writer is writing, it won't be able to grab it, so it will wait here. In that situation, since the first reader is waiting at this line, if another reader wants to come in, then it will have to wait on this line because the mutex has not been released by the first reader. So the second, third, fourth, all of those readers have to come and wait on this line outside. The first reader is waiting on this line here because the writer still has the read write mutex. If the writer releases that, then the first reader will be able to grab the mutex, read write mutex immediately, and then signal the plain mutex variable. When it does that, then it will come and start reading the document. Maybe the second, third, fourth, one of them will then be allowed entry inside because the mutex also has gotten released by the first reader. The second reader then does read count plus plus, takes the value of read count from 1 to 2. This condition will not be satisfied because read count is now 2. So the second reader will not grab the read write mutex. It actually cannot because it has already been taken by the first reader, and it is guaranteed that the writer cannot write now. The first reader has guaranteed that. So the second, third, fourth, up to all the rest of the readers who come in, they don't have to worry about the fact that while they are reading, the writer might start writing. That will not happen. Okay. So the first reader comes in and reads. The second reader also comes and reads. So maybe now there are 3 readers inside, they are reading. Okay. Let's just say one of the readers, not necessarily the first one. The first one, last one does not matter. Now there are 3 readers, all are equal. Some reader is done. It might be the second one to come, third one to come, or first one to come. Whosoever, does not matter. One reader is done. They want to come out of this reading process. What will they do? Since they will have to decrement the read count, they will have to again grab the mutex. They will do read count minus minus. So read count is now 2. Is read count equal to 0? No. That means that there are 2 more readers still inside the document. Okay. So should we give away the read write mutex? Should we give it up now? Since 2 more readers are there, then the reader who is trying to come out of the document will not signal this, because if it signals, then the reader might start writing when there are 2 more readers still in the system, right? We do not want that. Okay, when the second reader is done, then they will take the value of read count from 2 to 1. Okay. Now, is the read count equal to 0? No. That means it is not the last reader. One more reader is still there. Also, the read write mutex will not be signaled. Okay. So since there is this one last reader left, you will not signal the read write mutex because someone else will grab it and they will start writing. We don't want that. We still have that one last reader. As I told you, when there is this one reader, you cannot write. Okay, when the last reader is done, they will make the read count 0. This condition will be true. Then the read write lock will be given. Now the writer grabs the lock. If another reader wants to come to the top, again that reader will become the first reader, right? Now there are no readers in the document. They will wait on mutex. They will make read count 0 to 1 again. This condition will be satisfied. They will again wait on this line. Maybe the writer is taking a long time to write. So the first reader has to wait here. The rest of the readers will again have to wait outside because this mutex semaphore has not been released by the first reader. The first reader is actually inside waiting for the read write mutex, which the writer has right now. When the writer gives it up, the first reader comes in, second reader, all of them can come in freely. There is no problem. Once one reader is inside, multiple readers can come inside. All right, correct. So this is a very interesting problem. So here the thing is that there are 5 philosophers who are sitting around a table. There's some rice in front of them, and interestingly, there are only 5 chopsticks. Okay, for all 5 of them to start eating at the same time, they would need 10 chopsticks. One for their left hand, one for their right hand. 5 of them 10. But there are only 5 chopsticks on the table. So, for example, if I number the chopsticks like 0, 1, 2, 3, 4, and if I call this philosopher 0, 1, 2, 3, 4, then you can clearly see that if philosopher 0 wants to eat, they will have to pick up chopsticks 0 and 1. If 0 and 1 are already picked up, while P0 is eating, P4 and P1 cannot eat because P1's left chopstick is with 0 and P4's right chopstick is with 0. Can all of you see that?
Yes, sir.
Okay.
Yes, sir,
This
yes,
is the
sir.
problem. So we need to solve this problem and see how, if somebody is hungry, so most of the time the philosophers spend their time thinking. But if they're hungry, they'll start eating. But they can only eat if they have both the chopsticks with them, left and right. They cannot eat with just one. Okay. So we have the bowl of rice as the data set and an array of semaphores. This is an array. The chopstick is an array of 5 binary semaphores. All of the semaphores are initialized to 1. This semaphore basically means that if chopstick of 0 equal to 1, that means this chopstick is on the table. Similarly, if chopstick 4 is equal to 1, that means the 4th chopstick is on the table. If something is 0, that means that chopstick is being used by is in use by a philosopher. Okay, so with that understanding, let's figure out how we could solve this. Okay, so let me quickly copy this to this slide, maybe to this slide, and also this slide and this one for easier understanding. All right, now let's get started again. Okay, so what's happening here? Look at this. So the structure for philosopher I. Okay, so let me then number the chopsticks again. 0, 1, 2, 3, 4, and the philosophers also. This is philosopher 0, 1, 2, 3, and 4. Okay, so if philosopher I is running this program, then if they want to eat, what would they do? So for example, let's take the example of philosopher 0. So philosopher 0 would want to pick up chopstick 0 and chopstick 1. So for philosopher 0, I is equal to 0. So chopstick I is chopstick 0. So basically chopstick 0 is basically a semaphore and you can wait on it. If its value is 1, you will decrement the value to 0 and then you can continue. If its value is already 0, then you will have to wait. You will be stuck there. Okay, is this much making sense from the ideas of semaphores?
Yes, sir. Yes.
Yes, sir.
Okay, so you basically wait on chopstick 0 and then you wait on I plus 1, which is 0 plus 1 is 1, percentage 5 is 1. So 0 and 1. So your for any value of I, chopstick I is going to be their left chopstick and I plus 1 percentage 5. We do percentage 5 because there are only 5 chopsticks, right? After 4,
Yes, sir.
it will basically go to 0 again. So it goes round and round like that. So basically, this is the left chopstick, and this is the right chopstick. Okay. Okay. So you wait for the left one and the right one. Once you have both of them, you start eating. Once you are done, you put down the left chopstick, signal it. Basically, make its value 1. It's like putting the ticket back on the table, putting the chopstick back on the table, and then you signal the right chopstick. Okay. Then you start thinking until you are hungry again, and then you again start waiting for the left and right chopsticks, and you eat. Okay. So what is the problem with this algorithm? Think about this for 2 minutes and let me know what problem can happen. You know. Think about it. I think you're totally capable of answering this question. If you cannot,
So
then
one of the problem will be the consecutive philosopher will not be able to do something until its adjacent one doesn't complete it.
that is one problem. But yeah, that is one problem. But that is anyway going to be there for any solution. For any, that is itself the part of the question itself, right? If P0 is eating, then P1 and P4 can never eat. I mean, that is part of the problem. No solution can solve that. But what is the problem with this specific solution? Can you think of one corner case?
Sir, infinite waiting for 1 or 4.
How?
Alternate will not eat.
That's all fine. That is part of the problem. Alternates cannot eat. But when they put the spoon back, then they can eat. So if 0 is eating, 1 and 4 cannot eat. But once 0 is done eating, then 1 and 4 have a chance of eating. I mean, 1 can eat if 0 is not eating and 2 is not eating. Right? 4 can eat if 0 is not eating, 3 is not eating. 0 can eat if 1 is not eating, 4. So if the neighbors cannot eat, the neighbors are eating, then you cannot eat. That's okay. But so if you are eating, the neighbors have to wait for you. Once you put down sometime you will put the chopsticks back and then they can eat. Those are not problems. Those are part of the question itself. What is the problem? Well, let me tell you the problem. The problem is that, let's just say all the processes that run once and process P0 runs, it picks up this left chopstick. Then it is stopped by the scheduler. Then process P1 runs, it also picks up its left chopstick. So 0 picks up this chopstick, P1 then runs, picks up this chopstick, 2 picks up 2, 3 picks up 3, 4 picks up 4. So everyone, all the programs, they are able to run this first line of code, then they all pick up their left chopsticks. But then none of them will be able to pick up their right chopsticks because their right is somebody else's left, right?
Yes, sir.
All the processes are deadlocked. No one can eat. And they are all stuck because they will hold on to their left one. They're all trying to get the right one, but the right one is gone. So nobody can move from there. They're all stuck. Isn't that a big problem?
Yes, sir.
Okay, so that is a deadlock,
Yes.
right? It's a deadlock. Okay, so how can we handle the deadlock? We can handle the deadlock by allowing at most. Okay, we can handle deadlock by allowing maybe at most 4 philosophers to be sitting simultaneously at the table. If 4 of them are there, then a deadlock cannot happen. So let's just say P0 picks up this chopstick, P1 picks up this one, and P2 picks up this, and this philosopher is not there. Then at least this guy can pick up both, start eating, put down both of them, then this guy can start eating because it will then have both. It will put both of them, then this can eat, then this can eat. There is no deadlock then, right?
So P5 is not there. What it means? Like
I mean,
we have.
just read this statement. Allow at most 4 philosophers to be sitting simultaneously at the table. Instead of 5 philosophers, only have 4 philosophers sitting at the table. So I removed 1 philosopher from the game.
Okay. Okay.
So then what's going to happen? Even if this philosopher picks up this spoon, this philosopher picks up this spoon, this philosopher picks up this chopstick, but the last philosopher here can pick up both of them and eat. Once it is done, it will put both of them back. This philosopher here is waiting for the right spoon. Now it is available, then it can grab both and eat. Once it is done, it will put both of them back. This philosopher here was waiting for this right spoon. Now it can grab and eat. It will put it back. And finally, this philosopher can eat. Right? They are not going to be stuck indefinitely. right?
Yes. Yes, sir.
Okay, so if we remove one philosopher, then no deadlock will happen. Allow a philosopher to pick up the forks only if both are available. So it's like this. So if P0 wants to eat, it cannot only pick the left chopstick. It will first check if both of them are available. If yes, it will pick up both of them at one time. Then what will happen if P1 wants to eat, it won't be able to pick up just the right one because the left one is not there, it will not pick up anything. Then what will happen is that this one can then pick this and this. Then at least P0 and P2 can eat. Once they are done, then maybe P1 can do the check again. This time both the chopsticks are there, it can then eat it. So don't pick up one and then wait for the other one. If both are there, pick them up in one step. Otherwise, don't do anything. Right? Using this also, deadlocks will not happen. Right?
Yeah,
The picking up must be done in a critical section. If you are picking up the left and right, then no one else can be picking up anything else. It's not like when you picked the left, you checked, you're picking the left one, and then immediately it's like you're going to park at a place, you're backing up your car, and someone else comes and parks the car. You become angry, right? That should not happen here. If you have checked that both the spoons are there, then you have to pick them up at the same time. And while you are picking, your neighbor should not be able to come and say, oh no, I also want it. No, I have put my eyes on them, then I will grab them. Then also this will work.
So this kind of handling and which we did with previously, they are happening simultaneously or they are separate from each other?
Which one?
Sir, in which we are allowing only at most 4 philosophers to be sitting.
Here you don't need that. Here you don't need the fact that you have to pick up both at the same time. Here you can pick the left and then the right, even then deadlocks will not happen.
Okay. Okay, sir.
Right? In this solution, basically you're picking the left and then your process can stop in between. And someone else can take your right away. Then you are stuck. Right? But with five philosophers, a problem can happen. But with 4 philosophers, even with this solution, deadlocks will not happen because there is one less philosopher. At least one philosopher can get both the forks. At least one of them can get it. Right?
Okay.
Work it out. Okay? You'll understand what I'm trying to say. Or use an asymmetric solution. Like odd numbered philosopher picks up first the left chopstick, then the right. Even number philosopher picks up the right chopstick first and then the left chopstick. If you do this also, a deadlock will not happen. Okay? Well, let's see how that's the thing. So for example, this is even number, right? 0, 1, 2, 3, 4. So the even number guy, let's just say they pick up the left one first, then the right one. The odd number ones, they pick up the right one first, then the left one. So this can either go to this guy or this guy depending on who comes first. But at least one of them will get it, right?
Right, sir.
Then they can eat. When they will put it down, the other one will get it then. With a deadlock, no one can move. That's a big problem. Okay. Well, let's look at different problems that can happen with semaphores. Well, if a semaphore's value is usually 1 to begin with, right? It's a binary semaphore, it's a mutex, then its value will be 1. If it's a counting semaphore, its value can be like 7 or whatever. If you first signal and then wait, this is the wrong sequence. If you signal a mutex, then this 1 will become a 2. Then 2 people can simultaneously wait on it, which is not what it was intended for. Then 2 people can enter the critical section, which is totally wrong. So always wait. So if it's 1, make it 0, then signal, make it 1 again. It should always be 1 0 1 0 1. It should never become 2. So if you use this is going to be wrong. If you do wait 2 times, a second wait will never be satisfied. It is 1, you make it 0 in the first wait. Second time, this wait will be indefinitely blocking on this, right? This is also wrong. Or you omit the wait or signal in any way, shape, or form, right? The correct sequence should be wait and then signal. Or do a P operation, then a V operation. That's all. Never mix up these. Otherwise, deadlock and starvation can happen. वेट में क्या होता है, अगर एक हमारे पास एक सेमाफोर है, उसके ऊपर हम एक वेट ऑपरेशन चलाते हैं, तो वो क्या करता है? और किसी को पता है क्लास में वेट में क्या होता है?
वेट में हम लोग एक -1 करते हैं।
-1 ऐसे सीधा कर देते हैं बिना कुछ देखे?
नो सर
क्या check
उसमें
करते
जो म्यूटेक्स होता है वो ग्रेटर देन 0 होना चाहिए।
करेक्ट। तो अगर म्यूटेक्स में वेट में क्या होता है, हम देखते हैं कि म्यूटेक्स ये क्या है। म्यूटेक्स यहाँ पे जो है वो सेमाफोर एक इंटीजर वैल्यू होता है। हम वेट में क्या करते हैं, वेट पे वो नंबर लेते हैं। हम देखते हैं कि वाइल ये नंबर जब तक लेस देन इक्वल टू 0 है तब तक कुछ मत करो। अगर ये बड़ा हो गया 0 से तो इसको माइनस माइनस करके निकाल दो। ये होता है वेट। सिग्नल में क्या होता है, सिग्नल में बस इसको s प्लस प्लस करके निकालते हैं। ठीक है, ये पता होना जरूरी है। ये अगर नहीं पता है तो ये समझ में नहीं आएगा। और ये कैसे पता होगा, अगर पहले क्लास में ध्यान दे के सुने होते तो पता हो जाता, नहीं तो बुक में अगर पढ़ ले तो पता हो जाता। तो कुछ कोई बात नहीं है, आगे जाके पढ़ लो, समझ में आ जाएगा। कोई मुश्किल चीज नहीं है, ये बहुत आसान चीज है। ठीक है, ओके। तो पहले अगर हम सिग्नल करें तो क्या हो जाएगा?
सर
बोलो।
अगर वेट में s का वैल्यू 0 से ग्रेटर है तो एक ही बार माइनस माइनस होता है या लाइक अंटिल इट्स 0?
नहीं, अगर बाइनरी सेमाफोर है तो फिर बाइनरी सेमाफोर, काउंटिंग सेमाफोर, दो अलग अलग किस्म के सेमाफोर्स हैं, है ना। बाइनरी सेमाफोर में वैल्यू 0 और 1 होता है। काउंटिंग सेमाफोर में वैल्यू कुछ भी हो सकता है। मतलब मान लो अगर 4 है तो 4 हो सकता है, 3, 2, 1, 0 कुछ भी हो सकता है। अगर ये बाइनरी सेमाफोर है तो हम इसका वैल्यू यूजुअली 1 से शुरू करते हैं कि वो अवेलेबल है, कोई भी उसको ग्रैब कर सकता है। पहला जो आया वो उसको 0 करके छोड़ देगा, ये चेक करेगा ये तो गलत है, लेस देन इक्वल टू 0 नहीं है तो माइनस करके छोड़ देगा। तो कोई और जब आएगा तो यहाँ पे फंस जाएगा इस व्हाइल लूप में, वो माइनस नहीं कर पाएगा जब तक कि जो पहले लेके गया था वो उसको प्लस करके छोड़े। इसीलिए मैंने बोला कि पहले वेट करो फिर सिग्नल करो। कभी भी पहले सिग्नल फिर वेट मत करना, क्योंकि पहले सिग्नल अगर कर दिया तो वैल्यू 1 से तुम उसको 2 कर दोगे।
सर अगर काउंटिंग में हो गया तो लाइक सपोज 3 है वैल्यू s का,
हाँ,
तो सर माइनस अगर वेट किया तो माइनस होके 2 हो जाएगा।
2 हो जाएगा, फिर और 2 भी आ सकते हैं उसके बाद,
और 2 बार और वेट हो सकता है।
2 बार और वेट हो सकता है, बिना ब्लॉक करके 2 बार और वेट हो सकता है।
अच्छा ओके सर, उसके बाद एरर आएगा।
उसके बाद एरर नहीं आएगा, फंस जाएगा वो,
फंस जाएगा वो। एग्जैक्टली सर, वही बोल रहा हूं।
फंस जाएगा वो, फंस जाएगा जब तक कि कोई एक सिग्नल करके बाहर ना निकले। जब सिग्नल करके कोई बाहर निकलता है उसके बाद फिर कोई दूसरा कोई आके वेट कर सकता है। मैंने वेट में अगर फंसा होगा तो निकल जाएगा व्हाइल लूप से s माइनस माइनस करके।
सर तो सिग्नल का लिमिट नहीं है, जितना भी ऐड कर सकते हैं?
नहीं,
वेट
लिमिट है ना। सिग्नल का लिमिट क्या है कि हमारे पास अगर मान लो एक काउंटिंग सेमाफोर का मैक्सिमम वैल्यू 5 होना है।
अच्छा।
मैं तो 5 बार अगर वेट करूं तो मतलब एक बार वेट करने के बाद तो एक बार सिग्नल करें, इसके ऊपर अगर मैं 10 बार सिग्नल कर लूं तो इसका वैल्यू तो 15 हो जाएगा।
हाँ सर।
तो मेरा अगर नियम यह है कि एक रूम के अंदर 5 में से ज्यादा लोग नहीं आ सकते।
अच्छा, तो कैपेसिटी तक सिग्नल कर सकते हैं, उसके बाद वेट करना पड़ेगा?
करेक्ट, कैपेसिटी तक सिग्नल कर सकते हैं, उसके बाद वेट करना पड़ेगा। तो
अगर लाइक कैपेसिटी के बाद भी सिग्नल किया तो
वो गलत है, वो गलत हो जाएगा। मतलब वो सेमाफोर का मतलब नहीं रहेगा फिर।
अच्छा,
मान लो मैंने एक म्यूटेक्स बनाया है, म्यूटेक्स मतलब 0 और 1 होना चाहिए, पहले से वैल्यू उसका 1 है, तो कोई अगर आके पहले से उसको सिग्नल कर दे इसका वैल्यू 1 से 2 हो जाएगा।
हाँ सर।
उसका मतलब फिर क्या हो गया, फिर 2 लोग उस पर वेट कर सकते हैं।
ऐसे
फिर उसका मतलब क्या होगा, फिर 2 लोग क्रिटिकल सेक्शन के अंदर घुस सकते हैं एक साथ, है ना। तो फिर प्रॉब्लम हो गया, फिर जो जिस काम के लिए हमने सेमाफोर को लिया था वो काम वो कर नहीं रहा। फिर अगर मान लो 2 बार वेट कर लिया, वैल्यू उसका 1 था, एक बार वेट किया 1 से वो 0 हो गया, उसके बाद फिर से तुमने उसके ऊपर वेट अगर कर लिया सेम प्रोग्राम में, तो फिर तो इसके आगे तुम जा ही नहीं सकते।
हाँ सर,
कि अटक जाएगा, फिर किसी को तो सिग्नल करना पड़ेगा ना बीच में, तो तुमने किया नहीं है। तो ये दोनों गलत है। और कोई भी अदर सीक्वेंस में तुम अगर करोगे तो ये डेडलॉक और स्टार्वेशन हो सकते हैं बिल्कुल। तो ये है तुम्हारा सेमाफोर का प्रॉब्लम। इस क्लास में हिंदी कौन नहीं समझता? सब मतलब इंग्लिश में बोलना किसको जरूरत है? अगर कोई भी हिंदी नहीं समझता तो प्लीज क्लास में बोलिए अभी कि आपको हिंदी में समझ में नहीं आता, क्योंकि मुझे जो लगता है कि बाकी के बच्चों को हिंदी में ज्यादा समझ में आता है। और मुझे कोई प्रॉब्लम नहीं है हिंदी में बात करने में, मतलब जितना मैं ज्यादा अच्छे से बोल नहीं सकता, लेकिन आई थिंक आप लोगों को समझ में आ रहा होगा जितना भी बोल रहा हूँ।
यस सर, सब लोग जानते हैं हिंदी सर, अच्छे से
जानते हैं? अच्छा ठीक है।
यस।
तो अगर किसी को पता नहीं है तो मुझे बोल दे बीच में, क्योंकि मैं किसी को परेशान नहीं करना चाहता, लेकिन बाकी के लोगों को भी मतलब अंग्रेजी में जो जल्दी जल्दी से मैं काफ़ी जल्दी बात करता हूँ, तो इसीलिए कुछ लोगों को समझ में नहीं आता, फिर बाद में उनको रिकॉर्डिंग की ज़रूरत पड़ती है, फिर वो प्रॉब्लम हो जाता है। ठीक है, मैं हिंदी में बताता हूँ, आगे जाके किसी को समझ में ना आता मुझे बोले, मैं इंग्लिश में फिर से समझा दूंगा। ठीक है, तो अभी हम देखेंगे मॉनिटर्स के बारे में। तो मॉनिटर्स मतलब आप में से कितने लोगों ने ऑब्जेक्ट ओरिएंटेड प्रोग्रामिंग में काम किया, C++, जावा, इस टाइप के प्रोग्रामिंग लैंग्वेजेस में? किसी ने
C++ में किया था।
C++ में किया है? अच्छा ठीक है, अगर किया भी नहीं होगा तो कोई बड़ी बात नहीं है। मॉनिटर क्या है? एक एब्स्ट्रैक्ट डेटा टाइप है। जैसे कि आपने लिंक लिस्ट, क्यूज, टैग्स पढ़ा होगा। लिंक लिस्ट में क्या होता है? एक एब्स्ट्रैक्ट डेटा टाइप होता है। वो सी में कैसे होगा, C++ में कैसे करेंगे, जावा में कैसे लिखेंगे, वो बात की बात है। पहले से हमको बताना है कि एक लिंक लिस्ट में होता क्या है। एक स्ट्रक्चर होता है, उसके अंदर एक डेटा पॉइंट, एक डेटा रहता है और एक पॉइंटर होता है दूसरे नोड के लिए। ठीक है, डबल लिंक लिस्ट है तो आगे का एक नोड है, पीछे को जो उसके पहले है उसको लिंक करने के लिए एक होता है। ठीक है, बस वो एक एब्स्ट्रैक्ट डेटा टाइप हो गया। एब्स्ट्रैक्ट, हम वो कॉन्क्रीटली अंदर सी में कैसे उसको काम करता है, कैसे उसको लिखना है, उसके बारे में बात नहीं कर रहे हैं। हम ऊपर ऊपर से बता रहे हैं कि आइडिया क्या है। स्टैक में क्या होता है? एक अरे होता है जिसके अंदर एक टॉप ऑफ स्टैक पॉइंटर होता है, उसमें पुश कर सकते हैं, पॉप कर सकते हैं, वो एब्स्ट्रैक्ट डेटा टाइप हो गया। क्यू में क्या होता है? एनक्यू कर सकते हैं, डीक्यू कर सकते हैं, है ना? तो ये एब्स्ट्रैक्ट डेटा टाइप। सो सेमाफोर में आपने जैसा देखा कि प्रॉब्लम्स हो सकते हैं। आपने गलती से अगर सिग्नल पहले कर दिया, वेट बाद में कर रहे हैं तो प्रॉब्लम है, 2 बार वेट कर लिया तो भी प्रॉब्लम है। तो धीरे धीरे क्या होता है कि हम एप्लीकेशन प्रोग्रामर्स के लिए काम आसान करना चाहते हैं, हम उनके लिए मुश्किलें पैदा नहीं करना चाहते कि तुम टेस्ट एंड सेट यूज करो, कंपेयर एंड स्वैप यूज करो, तो वो गलतियां करेंगे। और ऐसे चीजों में गलतियां होने से क्या होता है कि जो रेस कंडीशंस होते हैं वो हमेशा होते नहीं है, और 100 बार में 2 बार होगा, और तुमको अगर वो कैच करना बहुत मुश्किल है। आगे जाके जब तुम लोग काम करोगे देखोगे कि जो रेस कंडीशंस है मल्टी थ्रेडिंग प्रोग्रामिंग में, उनको डीबग करना बहुत मुश्किल होता है, क्योंकि वो हमेशा रिप्रोड्यूसिबल नहीं होता। कभी कभी होगा, कभी कभी नहीं होगा, कभी वो वैल्यू ये निकल के आएगा, कभी वो निकल के आएगा, तो उनको पकड़ना काफी मुश्किल है। एक बार गलती कर देना, उसको ढूंढना बहुत मुश्किल हो जाता है। तो इसीलिए ये सब कामों में मतलब काम पूरा सॉलिड होना चाहिए, मतलब गलतियां होने का जो चांसेस है वो बहुत कम होना चाहिए। तो इसीलिए हमने सेमाफोर में देखा धीरे धीरे करके ऊपर आ रहा है। जैसे हमने देखा कि पीटरसन सोल्यूशन देखा, मैंने बोला कि चलो ये थोड़ा मुश्किल है, प्रोग्रामर्स इसको अच्छे से नहीं कर पाएंगे, तो इसीलिए हम आगे जाके हमने देखा कि चलो टेस्ट एंड सेट, कंपेयर एंड स्वैप इंस्ट्रक्शंस हार्डवेयर में हमने देखा, तो इसको यूज करना भी थोड़ा सा कंफ्यूजिंग था। तो ऊपर हम गए, हमने बोला कि ये एक्वायर बोल के एक फंक्शन है और रिलीज बोल के है, ये म्यूटेक्स हो गया। चलो इससे ऊपर हम क्या कर सकते हैं, हम सेमाफोर बना सकते हैं जो कि हमको काउंटिंग भी दे सकता है, बाइनरी भी दे सकता है, काउंटिंग भी दे सकता है, तो ये और बेहतर है। तो इसके ऊपर हमने देखा कि चलो इसमें भी गलतियां हो सकती है, कि क्या है कि तुमने सीक्वेंस बदल दिया, कोई डेडलॉक वेडलॉक करा दिया, जैसे कि इस स्लाइड में हमने देखा, ये सब कुछ हो सकता है। तो अभी हम मॉनिटर में आके पहुंचे, जो कि सबसे ज्यादा डेवलप्ड चीज है। क्या है मॉनिटर? मॉनिटर में क्या है आपका, ये है मॉनिटर का डेफिनेशन। इसके अंदर आपने मॉनिटर का नाम दे दिया। उसके अंदर क्या होता है, कुछ शेयर्ड वेरिएबल्स होते हैं, जो वेरिएबल्स की ये मॉनिटर के अंदर कोई भी एक्सेस कर सकता है। उसके अंदर कुछ प्रोसीजर्स भी है। प्रोसीजर्स क्या होता है, जो फंक्शन होता है आपका, सी में एक फंक्शन आपने लिखा, C++ में, जावा में एक मेथड लिखा आपने, तो वो प्रोसीजर है। ये प्रोसीजर एक लिमिटेड सेट ऑफ थिंग्स कर सकते हैं, मॉनिटर के अंदर ये रहते हैं, और जब ये प्रोसीजर चलता है ना, इसके अंदर जब कोड चलता है, ये कोड ये शेयर वेरिएबल को एक्सेस कर सकता है। ये वो शेयर्ड वेरिएबल्स के वैल्यू को रीड कर सकता है या उसको चेंज भी कर सकता है। ऐसे आप बहुत सारे प्रोसीजर्स इसके अंदर लिख सकते हैं। और ये मॉनिटर की जो वेरिएबल्स हैं, इनको इनिशियलाइज करने के लिए, जैसे कि कंस्ट्रक्टर होता है C++ में, जावा में, इनिशियलाइजेशन का कोड भी होता है। ये कोड पहले चलता है जब ये मॉनिटर काम करने के, कोई भी इसके अंदर घुसने के पहले हमको उसको इनिशियलाइज करना पड़ता है। और इसमें हम क्या करते हैं, ये जो शेयर्ड वेरिएबल्स हैं, इनका कुछ कुछ अगर इनिशियल वैल्यूज हमको सेट करके रखना है, तो वो इस कोड में हम कर सकते हैं। ठीक है, तो आगे जाके मैं आपको इसको और क्लियर कराऊंगा। ये देखिए, ये है, ये मॉनिटर का एक रिप्रेजेंटेशन है। जैसे कि आपको मैंने बताया कि शेयर डेटा कुछ है, ये इन सबको अवेलेबल है। ये मान लो ये एक प्रोसीजर है P0, तो ये एक कोड है जिसको कि एक प्रोसेस इसके अंदर आके उसको रन कर सकता है, और ये प्रोसेस जो है ये डेटा को रेफर कर सकता है, उसको रीड कर सकता है, उसको चेंज कर सकता है, कुछ भी कर सकता है। ये और एक प्रोसीजर हो गया P1, इसको भी एक प्रोसेस रन कर सकता है। ऐसे बहुत सारे चीजें हैं, इनको हम ऑपरेशंस भी बोल सकते हैं। एक इनिशियलाइजेशन कोड इधर बैठा हुआ है जो एक बार चलता है, पहले बार, और जो कि ये शेयर डेटा को इनिशियल वैल्यूज देता है। तो आप फिर पूछोगे कि ज्योति, ये जो मॉनिटर है ये अपना सी का कोई क्लास से फिर डिफरेंट कैसे है? ये तो पूरा वही हो गया कि कुछ डेटा है, कुछ मेथड्स हैं जो कि उनको चेंज कर सकते हैं। ये मॉनिटर का फायदा क्या हुआ? ये हमको क्रिटिकल सेक्शन प्रॉब्लम सॉल्व करने में हेल्प कैसे करेगा? ये ऐसे हेल्प करेगा कि इसका एक सबसे बड़ा कंडीशन ये है कि ये मॉनिटर के अंदर बस एक ही प्रोसेस एक टाइम में रन कर सकता है। अगर मान लो ये वाला ऑपरेशन जो है इसको अगर एक प्रोसेस चला रहा है, वो प्रोसेस का नाम है मान लो प्रोसेस एक्स, अगर ये प्रोसेस एक्स इसके अंदर रन कर रहा है तो बाकी कोई भी प्रोसेस इस मॉनिटर के अंदर रन नहीं कर सकता, बिल्कुल अलाउड ही नहीं है। वो सारे के सारे प्रोसेस बाहर क्यू में वेट करेंगे। जब ये प्रोसेस का काम खत्म होगा तब कोई और प्रोसेस को अंदर आने दिया जाएगा, फिर वो आके कोई एक ऑपरेशन को रन करेगा, शेयर डेटा को चेंज कर सकता है, कुछ भी कर सकता है। ऐसे करके हम गारंटी देते हैं कि एक टाइम में एक से ज्यादा प्रोसेस इसके अंदर कभी रन नहीं करते। ठीक है, आपको थोड़ा थोड़ा समझ में आ रहा है ये चीज?
जैसे तो ये प्रोसेस एक्स पूरा खत्म होगा या टाइम शेयर जैसे इंटरप्ट हो सकता है?
इंटरप्ट भी अगर होगा तो फिर से वो शुरू करेगा, वो पूरा खत्म होने तक उसको बाकी सबको वेट करना पड़ेगा।
अच्छा, पहले पूरा प्रोसेस एक्स खत्म होगा,
पूरा प्रोसेस खत्म होगा फिर जाएगा। लेकिन मैं आपको फिर से और एक कॉन्सेप्ट पे लेके जाता हूँ। ये है कंप्लीट डायग्राम मॉनिटर का। इसमें आपको ये देखने को मिलेगा कि कंडीशन वेरिएबल्स है। ये कंडीशन वेरिएबल्स होते क्या है? यहाँ पे जो एक्स और वाई हम देख रहे हैं ये कंडीशन वेरिएबल्स होते कहाँ हैं? ये बेसिकली आप ऐसे सोचो इसको कि मान लो ये P0 एक प्रोसेस है और P1 एक प्रोसेस है। मान लो P0 पहले इधर आके खड़ा हुआ है और P1 इधर आके खड़ा हुआ है। ठीक है, ये दोनों प्रोसेस अंदर जाने के लिए तैयार है। तो पहले हम P0 को बोलेंगे कि तुम अंदर आओ और चलना शुरू करो। तो मान लो P0 ये आके ये वाले ऑपरेशन को चलाना शुरू किया और ये यहाँ पे कंप्लीट नहीं कर पा रहा है क्योंकि इसको और एक चीज चाहिए जो कि P1 इसको दे सकता है। ठीक है, तो ये क्या करेगा, यहाँ पे एक कोई कंडीशन वेरिएबल के ऊपर वेट कर सकता है। तो वो क्या करेगा, वेट एक्स करेगा। जब ये वेट एक्स करता है ना, ये तुरंत ब्लॉक हो जाता है वो प्रोसेस फिर वेटिंग स्टेट में चला जाता है। वो कहां पे, तो मैंने आपको पहले बताया था कोई भी प्रोसेस को अगर वेट हम करते हैं ना तो सेमाफोर में जैसे हो गया बिजी वेटिंग नहीं होने का जो सेमाफोर, जिसमें कि एक लिस्ट में हम स्टोर करते थे प्रोसेस को कि कोई एक उसको वो ब्लॉक हो जाए, खुद को ब्लॉक कर ले, कोई और उसको फिर वेकअप करेगा। आपको याद है वो वाला चीज? ठीक है, तो वैसे यहां पे क्या होगा, जैसे P0 पूरा एग्जीक्यूट नहीं हो सकता क्योंकि उसको एक चीज चाहिए। यहां पे मान लो एक सम वेरिएबल में बनाता हूं, इसका नाम देते हैं सम। ये सम का डेटा कुछ है नहीं उसके अंदर, तो P0 बोलेगा कि मैं तो आगे बढ़ नहीं सकता, मुझे P1 का हेल्प चाहिए। P1 आके सम का वेरिएबल डालने के बाद ही मैं आगे बढ़ सकता हूं। तो वो क्या करेगा, ये एग्जीक्यूट करेगा, वेट एक्स करेगा। ये करने के टाइम तुरंत क्या होगा, ये P0 को सस्पेंड कर दिया जाएगा और वो कहां पे जाके वेट करेगा, यहां पे आ जाएगा। ये एक्स के कंडीशन वेरिएबल में एक क्यू है, वहां पे जाके वेट करना शुरू करेगा। मैंने ये नहीं बोला कभी कि मॉनिटर के अंदर कभी दो प्रोसेसेस नहीं हो सकते। मैंने ये हमेशा बोला है कि मॉनिटर के अंदर एक ही प्रोसेस एक टाइम पे रन कर सकता है, वेट बहुत सारे कर सकते हैं। तो ये P0 इधर आ गया। तो अभी हम यहाँ पे देखेंगे, चलो मॉनिटर के अंदर कोई चल नहीं रहा, P0 तो सो गया। अभी हम P1 को देखेंगे, तो P1 बोलेंगे तो तुम अंदर आओ। तो P1 आके इधर चलना शुरू किया और उसने काम करते करते ये सम के वैल्यू को इसने पॉपुलेट कर दिया। फिर करने के बाद ये क्या करेगा, सिग्नल करेगा। किसको, एक्स को। फिर जब एक्स को सिग्नल करेगा तो फिर P0 जाग जाएगा क्योंकि P0 तो एक्स के कंडीशन वेरिएबल पे वेट कर रहा था ना। तो P1 एक्स को सिग्नल करने का मतलब ये हुआ कि P0 जो भी प्रोसेस शुरू में है एक्स के क्यू में, तुम जाग जाओ, तुम जिसके लिए सो रहे थे वो भी अवेलेबल है, वो उपलब्ध है, तो तुम फिर से रन कर सकते हो। ये बात समझ में आई आप लोगों को?
यस सर।
ठीक है।
Yes,
अभी दो चीजें हो सकते हैं। आप मुझे पूछ सकते हो कि ज्योति अभी P0 P1 दोनों चलने लायक है, कौन चलेगा? दोनों तो एक साथ नहीं चल सकते क्योंकि P1 ने सिग्नल किया है, लेकिन P1 का आगे जाके फिर काम हो तो सकता है ना। उसने तो ये नहीं बोला कि मेरा काम खत्म हो गया। अब P0 भी तैयार है, वो बोल रहा है कि अरे मैं तो सो रहा था, सम के लिए, सम तो मेरे लिए अवेलेबल है, मैं भी चलने के लिए तैयार हूं अभी। तो दोनों में से कौन चलेगा? दोनों एक साथ नहीं चल सकते मॉनिटर के अंदर, एक को तो बंद होना पड़ेगा। तो दो चीजें हो सकते हैं, एक है तुम्हारा सिग्नल एंड वेट। ठीक है, इसमें क्या होता है कि क्यू अगर मतलब कोई कंडीशन वेरिएबल के ऊपर सो रहा है तो सिग्नल एंड वेट, उसका मतलब यह है कि P1 ने सिग्नल किया किसको, एक्स को, कि तुम P0 को जगाओ और चलना शुरू किया। तो सिग्नल जब होगा P1 में तो P1 तुरंत उसके बाद चलेगा नहीं, वो इधर रुका रहेगा, इधर फंसा रहेगा। वो P0 को चलने के लिए अलाउ किया जाएगा, ये चलेगा यहां तक। चलने के बाद जब खत्म होगा इसका काम, फिर वो बाहर निकल जाएगा। इधर वो मॉनिटर के बाहर निकल जाएगा, काम खत्म हो गया, नहीं तो वो कोई और कंडीशन वेरिएबल x हो गया, y हो गया, z हो गया, कोई दूसरा कोई कंडीशन वेरिएबल के ऊपर फिर से जाके वेट करे, मतलब फिर से सस्पेंड होने तक वो इधर वो बाहर चला गया, नहीं तो वो कोई दूसरे कोई कंडीशन के वेरिएबल के ऊपर फिर से जाके वेट करने लग गया, तब तक P1 चुप बैठेगा कि नहीं मैंने तुमको सिग्नल किया, तुम चलो रन करो, नेक्स्ट टाइम तक रुकने तक, तुम जब रुकोगे फिर मैं चलूंगा। Either P0 has to stop running or it has to start waiting on one of these condition variables. Then P1 will run. ये बात समझ में आई? सिग्नल एंड वेट, और एक होता है सिग्नल एंड कंटिन्यू। तो सिग्नल किसने किया? P1। तो जब P0 को सिग्नल मिला तो P0 तुरंत चलेगा नहीं। P1 ने सिग्नल किया, बोला मैं सिग्नल कर रहा हूं लेकिन आराम से उठो, मुंह धो फिर आओ, तुरंत आने की जरूरत नहीं है। तो P1 कंटिन्यू करेगा। P1 जब बाहर निकलेगा या P1 खुद जाके कोई कंडीशन वेरिएबल के ऊपर वेट करेगा, तब जाके P0 को चांस मिलेगा चलने के लिए। ठीक है, आप लोगों को समझ में आ गया कंडीशन वेरिएबल्स क्या है? कंडीशन वेरिएबल्स बेसिकली वेरिएबल्स होते हैं मॉनिटर के अंदर जिसके ऊपर हम वेट कर सकते हैं, मतलब हम बाहर भी वेट कर सकते हैं मॉनिटर के बाहर, ये अंदर आने के लिए ये एंट्री क्यू है। एक बार तुम अंदर आ गए, ये मतलब नहीं कि तुम सब कुछ कर लोगे। कोई चीज के लिए तुम अगर फंसे हुए हो तो तुम उसके ऊपर सो जाओगे, वेट करोगे उसके ऊपर जब तक कि कोई और इसको सिग्नल नहीं करता। तब सिग्नल करेगा फिर तुम रिज्यूम कर सकते हो। तो मॉनिटर एक चीज, इसमें शेयर डेटा है, ऑपरेशंस है, इनिशियलाइजेशन कोड है, बाहर है क्यू है। क्यू है क्योंकि एक बार एक एक करके हम अंदर छोड़ेंगे प्रोसेसेस को, और अंदर आने के बाद वो एक शॉट में चल जाएंगे, ऐसा कोई गारंटी नहीं है। वो कभी कभी वेट कर सकते हैं, तो वेट करेंगे वो कंडीशन वेरिएबल्स के ऊपर वेट करेंगे कोई और, फिर जब वो कंडीशन वेरिएबल को सिग्नल करेगा तब वो फिर रिज्यूम होंगे। समझ में आया?
सर यहाँ पे तो जैसे प्रोसेस P0 P1 पे डिपेंडेंट है तो फिर उसको वेट में डाल दिया, वेट।
हाँ।
पर अगर सर मान लीजिए फॉर प्रोसेस P0 उसको कोई डिस्क से डेटा चाहिए,
हाँ।
और वो क्यू में नहीं, एंट्री क्यू में, तब फिर सर क्या होगा?
फिर कुछ नहीं होगा, फिर P0 फिर वो क्यू में जाएगा, फिर वापस आएगा, फिर चलेगा ये, और कोई चलने नहीं वाला। वो डिस्क का कोई क्यू तो अंदर है नहीं ना। हाँ, तो फिर P0 बोलो।
और सर जब P0 आपका वेट कर रहा है X वाले क्यू में, तो
हाँ।
सर ये जो पहला ब्लॉक था ये अभी ऑक्यूपाइड रहेगा P0 से, बस ये सस्पेंड हो जाएगा?
नहीं, कोई ब्लॉक ऑक्यूपाइड नहीं होगा, मतलब सस्पेंड हो जाएगा। P1 आके फिर से वही वाला कोड चला सकता है, वो सेम कोड को चला सकता है, वो सेम फंक्शन को बिल्कुल चला सकता है। कोई ऐसा नहीं है कि ये वाला ब्लॉक ऑक्यूपाइड हो गया, कोई ब्लॉक ऑक्यूपाई नहीं करता। ये बस कोड है जो कि डिफरेंट थ्रेड्स ऑफ एग्जीक्यूशन आके उसको चलाते हैं।
ओके। और सर जो सिग्नल और वेट और सिग्नल और कंटिन्यू था, ये सर मॉनिटर की प्रॉपर्टी होगी?
हाँ, ये कंडीशन वेरिएबल्स के मेथड्स हैं। कंडीशन वेरिएबल के ये ऑपरेशंस अलाउड है उनके ऊपर, वेट और सिग्नल।
और सर दोनों चीजें एक साथ हो सकती हैं कि एक ही चीज मतलब एक मॉनिटर में पॉसिबल होगा कंडीशन वेरिएबल?
नहीं, देखो मॉनिटर के अंदर तो एक ही पीस ऑफ कोड रन कर सकता है, तो एक ही पॉसिबल है ना एक साथ।
मतलब या फिर सिग्नल वेट होगा या फिर सिग्नल कंटिन्यू होगा?
कंटिन्यू क्या? हाँ
सर दो।
ये हाँ कोई वो तो मतलब वो जो मॉनिटर का इम्प्लीमेंटर है वो चुनेगा ना कौन सा करना है।
ओके।
एक बार उसने कर लिया तो फिर सबको वही मानना पड़ेगा फिर।
ओके सर।
ओके, चलो हम मतलब ऑलमोस्ट लास्ट 3 स्लाइड्स पे आ गए। आज इसको खत्म करते हैं, शायद खत्म हो जाए ये, लेकिन ये काफी आसान है। देखो थोड़ा सा सोचना पड़ेगा इसके लिए, लेकिन इतना भी मुश्किल नहीं है। जो डायनेमिक फिलोसोफर प्रॉब्लम है उसमें डेडलॉक होता था, है ना, सेमाफोर यूज करने के टाइम। सारे फिलोसोफर्स को उनके लेफ्ट साइड के चम्मच को उठा लिया उन लोगों ने, फिर दाएं तरफ के चम्मच का तो उनका तो है नहीं, क्योंकि उनका जो दाएं तरफ का चम्मच है वो उनके दाएं तरफ के आदमी का लेफ्ट वाला चम्मच है ना। तो फिर डेडलॉक में हो गया। फिर कोई अपना लेफ्ट वाला स्पून नीचे नहीं रखेगा और राइट वाला स्पून तो उनके पास है नहीं, तो सबने अपना अपना लेफ्ट का उठा लिया और राइट का किसी का कुछ है नहीं, तो सारे एक दूसरे के ऊपर वेट कर रहे हैं, कोई आगे नहीं बढ़ सकता। उसका सोल्यूशन मॉनिटर से हो सकता है। देखो मॉनिटर एक ऐसा चीज है जो कि इनहेरेंटली हमको क्रिटिकल सेक्शन प्रॉब्लम सॉल्व करने के लिए हेल्प करता है, क्योंकि ये गारंटी देता है कि इसके अंदर एक ही प्रोसेस चल सकता है एक टाइम। वो बहुत बड़ा हेल्प है ना। वो उसका प्रॉपर्टी वही है कि इसके अंदर एक ही प्रोसेस चल सकता है, एक से ज्यादा प्रोसेस चल ही नहीं सकता। तो चलो देखते हैं कि मॉनिटर यूज करके ये डाइनिंग फिलोसोफर प्रॉब्लम कैसे सॉल्व हो सकता है। तो ये डाइनिंग फिलोसोफर प्रॉब्लम का हमने डेफिनेशन यहाँ पे शुरू किया, उसका नाम हमने दे दिया, मॉनिटर का नाम डाइनिंग फिलोसोफर्स। इसके अंदर हमने ये शेयर्ड वेरिएबल्स बनाया। ये क्या है? एक एनोमरेशन है जिसमें कि हमने एक अरे बनाया है 5 का। क्यों? क्योंकि 5 फिलोसोफर्स हैं, उनका जो स्टेट है वो सोच रहे हैं कि वो भूखे हैं कि वो अभी खा रहे हैं। ये तीनों स्टेट, थिंकिंग, हंग्री, ईटिंग, ये 3 स्टेट में से ये 5 फिलोसोफर्स कोई भी स्टेट में हो सकते हैं, है ना? ये समझ में आ रहा है? ये अरे
यस सर।
ठीक है, ये 5 फिलोसोफर्स है, उनका स्टेट है। मतलब कोई थिंकिंग हो सकता है, कोई हंग्री हो सकता है, कोई ईटिंग हो सकता है, ये उनका स्टेट मेंटेन करता है। और हमने एक कंडीशन वेरिएबल का एक अरे बनाया है सेल्फ का। ये देखोगे ये क्यों यूज होता है, लेकिन ये 5 अलग अलग कंडीशन वेरिएबल्स हैं। सेल्फ 0 फिलोसोफर 0 के लिए है, और सेल्फ 4 जो है वो फिलोसोफर 4 के लिए है। ये हम देखेंगे ये क्यों यूज होता है, तुम देखो। चलो इसका इनिशियलाइजेशन कोड देख लेते हैं। ये तो एक बार चलता है। ये क्या क्या है, इसने एक लूप चलाया और लूप के अंदर ये सारे फिलोसोफर्स के स्टेट को इसने थिंकिंग कर दिया। अभी कोई भूखा नहीं है, कोई खाना नहीं खा रहा, सारे सोच रहे हैं। ये समझ में आया इनिशियलाइजेशन कोड?
Yes, sir.
ओके, तो अभी चलो मान लो कि प्रोसेस जो P0 है उसको भूख लगा, ठीक है? तो ये मैं नंबर लिखता हूं यहाँ पे। ये है 0 1 2 3 4। ये है फिलोसोफर 0 1 2, ठीक है? तो चलो फिलोसोफर 0 को भूख लगा, वो क्या करेगा? पिकअप करेगा, मतलब स्पून उठाने की कोशिश करेगा। आई वैल्यू उसका 0 है, फिलोसोफर 0 है वो, तो वो अपने आप को फिर हंग्री घोषित करेगा कि मैं तो हंग्री हूं। अब खुद के स्टेट को उसने चेंज कर लिया। फिर वो एक टेस्ट ऑपरेशन को कॉल करेगा आई इक्वल टू 0 करके। चलो टेस्ट देखते हैं क्या करता है। ये है टेस्ट का कोड। मैं फिर से यहां पे नंबर लिख देता हूं। ठीक है, ये टेस्ट को कॉल किया गया है आई का वैल्यू 0 देके। ये क्या चेक कर रहा है? अगर आई प्लस 4 परसेंटेज 5, ये उसका लेफ्ट वाला स्पून है ना? आई प्लस 4 परसेंटेज 5 क्या होगा इस केस में? 4। आई प्लस 4 परसेंटेज 5, ये इसका ये क्या है? आई प्लस है 0 4 होगा, तो मतलब फिलोसोफर 4। तो अगर फिलोसोफर 4 खाना खा नहीं रहा, अगर मैं खुद भूखा हूं और आई प्लस 1 परसेंटेज 5, वो क्या है? वो 1 हो गया, मतलब फिलोसोफर 1। और फिलोसोफर 1 भी अगर खाना नहीं खा रहा, तो मेरे 2 नेबर्स खाना नहीं खा रहे हैं और मैं खुद भूखा हूं, तो मैं अभी ईटिंग स्टेट में चला जाऊंगा, ठीक है? और मैं अगर पहले मेरे खुद के कंडीशन वेरिएबल के ऊपर वेट कर रहा था, ये क्या हो सकता है कि पहले बार तो भूखा नहीं हुआ होगा, क्या पता बीच में कभी भूखा हो गया हो, लेकिन क्या पता इसके आजू बाजू के लोग खाना खा रहे हो तो इसको शायद चम्मच मिला नहीं होगा, तो इसीलिए वो खुद के कंडीशन वेरिएबल के ऊपर वेट कर रहा होगा, सो रहा होगा, है ना? कंडीशन वेरिएबल काम तो वही है कि प्रोसेसर्स को वो वेटिंग स्टेट में रखता है जब तक कि कोई उनको सिग्नल ना करे। इतना समझ में आ रहा है तुम लोगों को?
यस सर।
ठीक है, तो ये अभी अपने आप को जगा रहा है। वो बोल रहा है कि देखो जग जाओ, क्योंकि देखो मेरे बाएं तरफ का आदमी खा नहीं रहा, मेरे दाएं तरफ का जो फिलोसोफर है वो भी नहीं खा रहा, और मैं खुद भूखा हूं, तो मैं अभी ईटिंग स्टेट में जाऊंगा, दोनों चम्मच उठा के मैं खाऊंगा और खुद को सिग्नल करूंगा। देखो ये भी तो दोनों चम्मच उठा के खाएगा, ये खुद एक टाइम में ही होगा। देखो ये जब टेस्ट चला रहा है, ये मॉनिटर के अंदर गारंटीड है कि कोई अदर प्रोसेस चल भी नहीं रहा होगा, तो ये एक शॉट में उठा सकता है 2 चम्मच, जो कि हमारा एक सोल्यूशन था यहाँ पे कि दोनों को एक साथ उठाने के लिए चांस दो। ये वाला याद है? ये वाला हम यहाँ पे कर रहे हैं, ठीक है? समझ में आ रहा है?
यस सर।
ओके, तो इसको फिर और देखते हैं, ठीक है? तो यहाँ पे क्या किया? खुद को टेस्ट किया, बोला कि मेरे बाएं तरफ का जो फिलोसोफर है वो खाना ना खा नहीं रहा है, नॉट इक्वल टू ईटिंग, मैं खुद भूखा हूं, और मेरे राइट साइड में जो बैठा है वो भी खाना नहीं खा रहा, तो मैं खुद को ईटिंग स्टेट में लेके जाऊंगा। और अगर मैं सेल्फ को सिग्नल करना, लेकिन तुम पूछोगे अरे सिग्नल कैसे करेगा? तो चल तो रहा है ना, सिग्नल कैसे करेगा? तो सिग्नल अगर वेट कर भी नहीं रहे हो ना, तो सिग्नल यहां पे कर सकते हो। देखो यहाँ पे कौन चल रहा है? यहाँ पे प्रोसेस P0 चल रहा है और वो खुद को सिग्नल कर रहा है। उसका क्या ही मतलब हुआ? कुछ ज्यादा मतलब नहीं है उसका। The very fact that process P0 itself is running means that it is not waiting. ये बात समझ में आई?
यस सर।
P0
Yes.
खुद चल रहा है तो वो कहीं पे तो वेट कर नहीं रहा होगा, वो एक्चुअली वेट कर भी नहीं रहा था, वो पहले भूखा नहीं था, वो पहले भूखा नहीं था, अभी पहली बार भूखा हुआ, अंदर आया और तुरंत उसको चांस मिल गया कि लेफ्ट वाला खा नहीं रहा, राइट वाला खाना खा नहीं रहा, वो खुद भूखा है, तो वो पहले वेट नहीं कर रहा था। तो ये जो फिजूल का इसने सिग्नल किया ना, ये फालतू में किया, इसका कोई इफेक्ट नहीं होने वाला इसका, ठीक है। चलो, तो खुद को इसने ईटिंग कर दिया, तो फिर क्या है, टेस्ट करके ईटिंग स्टेट में चला गया। लेकिन ये हमेशा ऐसा होगा क्या? कोई गारंटी है? ऐसा भी हो सकता है कि टेस्ट करने के टाइम क्या पता ये बाएं वाला जो P4 है वो खाना खा रहा हो। अगर वो खाना खा रहा है P4, तो P0 खा सकता है क्या उस टाइम पे?
No, sir.
नहीं खा सकता है, तो अपने आप को वो ईटिंग नहीं कर सकता, अपने आप को वो ईटिंग घोषित नहीं कर सकता। तो अगर वो ईटिंग अभी भी वो खाना खाने का उसका मौका नहीं मिला उसको, तो वो वेट में चला जाएगा। देखो, अब ये खुद के कंडीशन के वेरिएबल के ऊपर वेट करा रहा है। तो मतलब हमने एक कंडीशन वेरिएबल का अरे बनाया था ना, ये वाला,
यस सर।
तो ये 0 के लिए है। तो वो क्या किया, प्रोसेस P0 ने यहाँ पे आके वो सो गया। चलो, मैं भूखा हूं लेकिन मेरे आजू बाजू के लोग खा रहे हैं, मैं सो गया इधर, ठीक है। अगर कुछ टाइम के बाद, अच्छा मान लो P4 खा रहा था, P4 खाना खा रहा था और और कोई नहीं, कोई और खा, तो P4 खा रहा था इसीलिए P0 खाना खा नहीं पाया। चलो, अभी P4 का खाना हो गया, तो वो क्या करेगा, वो पुट डाउन करेगा, है ना, वो अपने चम्मच को नीचे रखेगा और वो आई को किस वैल्यू से कॉल करेगा, 4 से, जो अपने आप को वो फिर थिंकिंग घोषित कर देगा कि चलो मैं तो अभी थिंकिंग हो गया, खाना खा लिया मैंने, मैं अभी थिंकिंग मोड में चला गया। उसके बाद वो क्या करेगा, अपने I+4%5 बोले तो वो अपने लेफ्ट साइड के और राइट साइड के, ये लेफ्ट वाला हो गया और ये राइट वाला हो गया, इन दोनों फिलोसोफर्स के लिए वो खुद से ये टेस्ट वाला फंक्शन को कॉल करेगा। क्यों कॉल करेगा? अरे जो चम्मच रख रहा है उसी का ही तो काम है ना किसी और को सिग्नल करने के लिए, नहीं तो फिर कौन सिग्नल करेगा? P0 खुद के लिए अभी सिग्नल नहीं कर सकता, वो सोने चला गया है। और वो क्यों सोने गया था? क्योंकि P4 खाना खा रहा था, तो P4 का रिस्पॉन्सिबिलिटी है ना कि P0 को जगाए फिर से, है ना,
यस सर।
है
Yes,
कि
sir.
नहीं, है कि नहीं? हाँ, तो P4 क्या करेगा, अभी टेस्ट को कॉल करेगा I+4%5, ये I+4%5 क्या है, 4 + 4 8%5 है 3, तो वो इसको देखेगा कि इसके चम्मच रखने के कारण क्या ये पॉसिबिलिटी जाग रहा है कि P3 फिर से खाना खा सके, ये टेस्ट करेगा वो। चलो, अभी P4 ने यहाँ पे अभी P4 चल रहा है, जो प्रोसेस चल रहा है वो P4 चल रहा है, लेकिन जो I के वैल्यू को कॉल किया वो I का वैल्यू है 3, ठीक है, ये I का वैल्यू 3 है। तो अभी हम देख रहे हैं ये पॉसिबिलिटी कि P3 खाना खा सकता है क्या, ये हम टेस्ट कर रहे हैं। ये टेस्ट कौन करवा रहा है? P4 टेस्ट करवा रहा है P3 के लिए। ये समझ में आ रहा है तुमको?
सर P4 तो चल गया ना, तभी तो फिर टेस्ट करवा रहे हैं।
P4 चल रहा है अभी, P4 अभी चम्मच रख रहा है, लेकिन चम्मच रखने के बाद उसका रेस्पॉन्सिबिलिटी बढ़ता है कि वो अपने आजू बाजू के लोगों को जगाए।
अच्छा, पूरा पुट डाउन, यस सर,
समझ गए?
यस सर, यस।
हाँ, तो वो जगा रहा है, अभी वो लेफ्ट वाले को देख रहा है, उसका लेफ्ट में कौन बैठा है, P3, वो देख रहा है कि P3 खाना खा सकता है क्या। यार, इसने चम्मच रख लिया, इसका मतलब गारंटेड है क्या कि P3 खाना खा ले? क्या पता P3 क्या पता P3 भूखा ना हो, क्या पता P2 खाना खा रहा हो तो P3 खा नहीं सकता, है ना। तो वो I=3 करके टेस्ट करेगा। चलो देखते हैं, तो अभी I=3 है, तो I+3 + 4 7%2 वो 2 हो जाता है। तो अगर तो 3 तब खाना खा सकता है जब 2 खाना खा ना रहा हो और वो P3 खुद से भूखा हो और 4 खाना नहीं खा रहा। 4 तो खाना खा ही नहीं रहा क्योंकि 4 ने अपने आप को तो थिंकिंग कर दिया इधर, 4 खाना नहीं खा रहा, लेकिन ये गारंटी नहीं है कि 2 खाना नहीं खा रहा। तो ये तीनों के तीनों कंडीशन अगर सेटिस्फाइड हैं तो हम 3 को जगा देंगे, लेकिन 3 एक्चुअली भूखा था नहीं, P0 खाना खा रहा था और P0 भूखा था, लेकिन P0 भूखे पेट पे सो गया है। तो चलो ये P3 अभी हंग्री है ही नहीं, तो ये कंडीशन फॉल्स हो गया। तो P4 और क्या करेगा, चलो इसको तो टेस्ट कॉल कर दिया, जिसको जगाना था जगा दिया, किसी को जगाया नहीं, P3 तो सो ही नहीं रहा था, वो हंग्री है ही नहीं। चलो अभी I+1 परसेंटेज 5 करके कर रहा है। ये I+1 क्या है, I इधर 4 है, 4+1 5 परसेंटेज 5 0, तो ये 0 करके कॉल किया I को। तो अभी ये इसके लिए चेक कर रहा है कि 0 खाना खा पाएगा क्या, ये I का वैल्यू अभी 0 है, तो 0 है, तो 0 + 4 परसेंटेज 5 है 4। तो दिखता है कि P4 खाना खा रहा है, नहीं P4 तो खाना नहीं खा रहा, क्योंकि उसने अपने आप को थिंकिंग कर रखा है। क्या P0 हंग्री है, हाँ है। P0 ने तो खुद को हंग्री करके वो सोया हुआ है, उसके कंडीशन वेरिएबल खुद के स्टेट को उसने हंग्री कर रखा है, वो भूखा सोया है। और P1 खाना खा रहा है क्या, 0 + 1 परसेंटेज 5, P1 नहीं, P1 भी खाना नहीं खा रहा, वो थिंकिंग में है। तो चलो, तो हम क्या करेंगे, सेल्फ आई मतलब P0 को सिग्नल करेंगे। क्या हो गया फिर, ये सिग्नल हो गया, इसको सिग्नल मिल गया, तो P0 जाग गया, ठीक है, मतलब P0 को चांस मिल गया कि P1 खाना नहीं खा रहा, P4 खाना खा रहा था, लेकिन अभी उसने चम्मच नीचे रख दिया और तुमको वो जगा रहा है, तो जाग जाओ खाना खाने के लिए, हंग्री हो तुम। तो P4 फिर निकल जाएगा, P4 के निकलने के बाद P0 फिर रेडी है चलने के लिए। P4 कहां से चलना शुरू करेगा, P0 ये यहां से टेस्ट से निकल के बाहर आएगा, यहीं पे फंसा हुआ था ना वो, सॉरी ये वेट में वेट कर रहा था, यहां पे वेट कर रहा था, तो पिकअप से बाहर निकल आएगा, खाना खाएगा। जब वो पुट डाउन करेगा, फिर वो अपने आजू बाजू को टेस्ट करेगा कि चलो मैंने खाना खा लिया, तुम लोगों को खाना खाना है क्या, ये 1 और 4 को फिर टेस्ट करके देखेगा। समझ रहे हो, बेसिक आइडिया समझ में आ रहा है सबको?
हाँ सर।
ठीक है, तो इसको थोड़ा सा अच्छे से स्टडी करो, तुमको अच्छे से समझ में आएगा। इसका मतलब मोटा मोटी ये बोल रहा है कि तुमको अगर खाना खाना है, खुद को हंग्री घोषित करो, टेस्ट करो कि तुम्हारे दाएं बाएं दोनों लोग खाना खा रहे हैं क्या। अगर वो खाना खा रहे हैं तो खुद को भाई तुम वेट करो, अपने खुद के कंडीशन वेरिएबल पर वेट करो। कोई अगर खाना खाना खत्म किया, वो पुट डाउन करेगा, अपने आप को वो ईटिंग स्टेट से थिंकिंग स्टेट को लेके जाएगा, फिर वो क्या करेगा, कोशिश करेगा कि अपने बाएं तरफ के फिलोसोफर को जगाए, देखे कि वो अभी खाना खाने के स्टेट में है कि नहीं। वो कब खाना खा पाएगा, उसके आजू बाजू में, वो तो तुम तो उसके एक बाजू हो, उसका और एक बाजू भी है उस साइड। अगर दोनों नॉन ईटिंग स्टेट में है, दोनों अगर थिंकिंग स्टेट में है और वो खुद भूखा है और वो वेट कर रहा है, फिर उसको जगाओ, उसको जगाओ लेफ्ट वाले को, राइट वाले को भी इन्फॉर्म करो, क्या पता वो भी सो रहा होगा भूखा पेट, क्योंकि तुम्हारे पास चम्मच थे ना, क्या पता तुम्हारे लेफ्ट और राइट दोनों को भूख लग गई होगी बीच में, दोनों सो रहे होंगे, तो दोनों को जगाने का काम तुम्हारा है। समझ गए?